The RUV light moves across black water and catches almost nothing at first. A few white particles cross the frame, each one bright for a moment, then gone. There is no bottom under the vehicle, no surface above it, only depth, cable, pressure, and a machine holding its position in a place where the sun has already ended. Then, something appears at the far edge of the beam. It is not rushing. It is not performing for the camera. It hangs in the water as if it has been waiting there longer than the light has existed. The animal turns, and the first thing that seems strange is not its mouth, or its teeth, or the shape of its body. It is the way it does not look back. Its eyes are small, reduced, or hidden in skin. In another fish, those eyes might seem like the center of the face. Here they feel almost secondary, less important than the line of the body, the spread of the fins, the pale sensory threads reaching into the current. The camera has entered a world where vision is no longer the first language. This is the midnight zone. Not because the water is empty, and not because life has failed here, but because sunlight cannot follow the ocean down this far. Above, the surface is full of glare and color. Lower down, blue light survives after red and orange have disappeared, but by about 1,000 meters, even that remaining light is gone. The ocean becomes a volume of permanent darkness, stretching downward for kilometers, and inside it are hunters that have learned to find food without seeing in the way surface animals see. They are often called blind, but that word can be misleading. Some have eyes that are nearly useless. Some have eyes that are small, but still able to detect a faint point of living light. Some do not hunt with vision first, but with touch, vibration, smell, pressure changes, or the shape of moving water. Some do not need to search very far at all. They let the current bring the world to them. If the hidden ocean is what brings you here, this channel will keep following the dark water. Because in the deep sea, even a creature that cannot see in the ordinary sense may not be lost. It may be reading the ocean through systems we barely notice at the surface, where light makes us forget how much information water itself can carry. A fish swimming through darkness pushes a faint pressure wave ahead of it. A shrimp beating its legs disturbs the water in a pattern that does not last long, but lasts long enough. A wounded animal releases chemicals into the current. A falling carcass changes the behavior of scavengers before any camera finds it. In the midnight zone, a hunter does not always need an image. It needs a direction, a vibration, a trace, a chance. The bathypelagic zone begins around 1,000 meters and extends to roughly 4,000 meters. In many parts of the ocean, that range is still open water, with no floor nearby. In other places, continental slopes, canyons, and seamounts rise into it, giving animals surfaces, currents, and edges to use. The pressure increases by about 1 atmosphere for every 10 meters of descent, so at 1,000 meters the pressure is already about 100 times what the body feels at the surface. At 4,000 meters, it is several hundred atmospheres. Yet the animals here are not crushed, because they are not built like surface machines lowered into depth. Their tissues contain water. Their bodies avoid large gas spaces. Their proteins, membranes, and skeletons work under pressure in ways that surface animals cannot easily imitate. The deep sea does not break them by force. It is their home, and the pressure is part of the home. Cold is another condition, but not always a dramatic one. In much of the deep ocean, temperature stays low and stable. There are no daily heat waves, no sunlight warming the water at noon, no seasons passing through the body of a fish in the way they pass over land. Stability can be useful. It can also make life slow. Metabolism may be reduced. Growth may take longer. A meal may have to last. A missed hunt may matter more than it would in a shallow reef. The most important limit is food. There is no photosynthesis in the midnight zone because there is no sunlight to power it. Most energy begins far above, where plankton grow in the surface layers. What reaches the deep may arrive as sinking particles, dead cells, fecal pellets, mucus, shed shells, fragments of animals, or the bodies of creatures that die while migrating between layers. This falling material is called marine snow, but it is not soft in the way the name suggests. It is the slow delivery system that keeps much of the dark ocean alive. In a camera beam, marine snow looks gentle. It drifts downward in pale flecks, turning slowly, as if the water itself is shedding dust. But each particle has already been handled by life. It may have been part of a plankton bloom, then eaten by a copepod, repackaged into a fecal pellet, colonized by microbes, broken apart by small animals, and sent downward again. By the time it reaches the midnight zone, it has become food for creatures that cannot afford to waste much. For predators, this means prey is uneven. It is not spread like grass on a field. It comes in layers, migrations, patches, odors, flashes, and accidents. A lanternfish moving too low, a squid stunned by something unseen, a shrimp crossing the wrong current, a body falling from above. A deep sea hunter is shaped by that uncertainty. Its senses are not designed for abundance, they are designed for rare information. This is why blindness in the midnight zone is not simply a weakness. In the absence of sunlight, large image-forming eyes can become expensive structures. They need tissue, nerves, energy, and space. If they cannot gather useful information, they may shrink across generations. In some animals, the lost investment is moved elsewhere, into smell, touch, lateral line systems, long fin rays, or the ability to detect faint electrical or mechanical signals. The lateral line is one of the most important senses in fishes, and in darkness it becomes especially valuable. It is a system of canals and sensory cells along the body and head, tuned to movement and pressure changes in the surrounding water. To a fish, it can reveal nearby motion without sight. It can help detect current, obstacles, predators, and prey. In the deep sea, where light is scarce or absent, the shape of disturbed water may be as useful as a shadow. Scientists do not see most deep-sea hunts directly. They infer many of them from anatomy, stomach contents, behavior in rare footage, and comparison with related animals. A fish with long tactile rays is not watched eating every night. An anglerfish with a glowing lure is not followed through its whole life. A dragonfish stomach may reveal prey, but not the exact moment of capture. The deep sea gives evidence in pieces. Those pieces are still enough to show that hunting in darkness has many forms. Some animals wait, some drift, some cruise slowly with mouths ready, some stand above the sediment on modified fins. Some make light, some hide their light until the instant it matters, some are almost invisible until prey is already inside the mouth. One of the clearest examples is the tripod fish, Bathyptera agralidar, a deep-sea fish often seen standing above the seafloor on long, stiff extensions of its fins. It does not stand like a land animal, with weight supported against air and gravity. It props itself in water, using elongated fin rays and the tail to raise the body above the sediment, facing into the current. Its eyes are reduced. Its pectoral fins carry sensitive feelers that extend forward into the moving water. The posture makes sense when food is carried by current. The fish does not need to chase everything it eats. It waits where the water moves past, lifting the body just high enough for drifting animals to come within range. The long feelers detect contact or movement. The head turns. The mouth opens. A small crustacean that never saw a predator in front of it becomes part of the seafloor food web. In ROV footage, a tripod fish can look almost artificial. The body is still, balanced on thin struts, as if someone placed it there. The fins do not flutter constantly. The animal seems paused between events. But this stillness is work. Holding position saves energy. Facing the current turns the environment into a delivery system. The fish is not blind in a helpless way. It is blind in a habitat where waiting may be more efficient than searching. This is one of the hardest things to keep in mind when looking at deep-sea animals from the surface. Their bodies often appear strange because we are not seeing the problem they solve. A long fin ray looks fragile until it is understood as a sensor. A huge mouth looks grotesque until it is understood as insurance against rare meals. A tiny eye looks primitive until the darkness around it is considered. The seafloor of the deep ocean is not flat in a simple sense. Even abyssal plains are crossed by small rises, burrows, tracks, shells, carcass remains, and patches of different sediment. Continental slopes and canyons can be much more complex. They collect organic material. They funnel currents. They create ledges, walls, soft basins, and places where prey can concentrate. For a hunter that does not rely on sight, the structure of the current can be as important as the structure of the ground. A canyon wall may deflect water upward. A seamount may compress flow around its sides. A trench slope may carry particles downslope after a disturbance. These movements are not dramatic in the way storms are dramatic, but they matter. A predator can place itself where food is more likely to pass. In the deep sea, geography is not only landscape, it is a way of sorting hunger. There are also hunters in the open water that cannot wait on the bottom. They live suspended in the black volume between surface and seafloor. For them, there is no rock to hide behind, no plant cover, no burrow, no reef. A small fish in the midwater is exposed in every direction. It must find food while avoiding becoming food. And in that space, sight becomes complicated. The darkness is not completely dark to the animals that live there. It is interrupted by bioluminescence, the living light produced by many marine organisms. A copepod may flash when disturbed. A jellyfish may release a glowing cloud. A squid may shine from organs in its skin. A fish may use light along its belly to hide its silhouette from animals below. A predator may carry a lure that glows because bacteria live inside it. In the deep water column, bioluminescence is not decoration. It is one of the main currencies of information. It can reveal, deceive, attract, warn, confuse, or conceal. To a human looking at footage, a flash may seem like a beautiful accident. To another animal, it may mean danger, prey, mate, wound, or opportunity. This means some midnight zone hunters are not blind because light is absent. They are hunting in a world where light exists, but in brief points and signals rather than daylight images. Their eyes may be tuned to detect those points. Their bodies may be black to absorb light. Their lures may imitate something edible. Their photophores may turn the body into a false sky. Deep-sea anglerfishes are the most familiar example of this kind of predation. In many species, the female carries a modified dorsal spine that ends in a lure, or esca, often containing bioluminescent bacteria. The lure hangs near the mouth. When a small fish or crustacean approaches the glow, the anglerfish can open its jaws and engulf the prey in a quick suction movement. It is not a chase in the ordinary sense. It is a trap built into the face. The word lure can make the animal sound theatrical, as if it is consciously pretending to be something else. The reality is simpler and more powerful. A point of light in a dark ocean is information. It draws attention because many animals have evolved to respond to light. Sometimes light means food. Sometimes it means another living thing small enough to eat. The anglerfish exploits that response by placing the signal where a mouth can close around it. A female anglerfish in the beam of an rov often seems almost motionless. The body is dark and rounded. The mouth is large. The teeth are long and angled inward, less like cutting blades than a cage designed to stop escape. The lure may hang ahead of the mouth or move slightly. Around it, the water continues carrying snow and tiny animals past the camera. The hunt may take hours. It may fail many times before it works once. This matters because deep-sea predators are not constantly winning. They are often wading through long periods of nothing. A successful design in the midnight zone is not the one that attacks most dramatically. It is the one that can endure the time between attacks. The anglerfish body is built around that economy. It reduces the need to swim. It lets prey spend the energy of approach. There are many kinds of anglerfish, and their lives are not all the same. Some live on the seafloor. Some live in open water. Some are known mostly from specimens damaged by nets or found at the surface after death. Some have been filmed alive only rarely. The most famous deep-sea forms are usually females, because the males can be much smaller and in some groups live in a very different way. Male deep-sea anglerfish may search for females using scent and other cues. In some species, when a male finds a female, he bites onto her and remains attached. In the most extreme cases, tissues fuse and he becomes dependent on her circulation, providing sperm when she is ready to reproduce. This is often presented as grotesque, but it is also an adaptation to scarcity. In the deep open water, finding a mate can be so unlikely that letting go may be the greater risk. The same darkness that makes hunting difficult makes reproduction difficult. A predator may be able to wait for prey, but a species cannot wait forever for mates. The body of the male becomes a solution to distance, dilution, and chance. It is small because smallness costs less. It searches because searching is its role. It attaches because, in that world, an encounter is too rare to waste. Blind hunters are not only shaped by prey, they are shaped by loneliness, by the size of the water, by the fact that an animal can live its whole life surrounded by darkness and still need to find another member of its own species at the right time. The midnight zone is not just a hunting ground, it is also a problem of communication. Light can solve part of that problem, but it can also create danger. A glow that attracts prey may attract predators. A flash that reveals a mate may reveal a body to something larger. For many deep-sea animals, light must be controlled carefully. It appears in organs, patterns, lures, or clouds. It is hidden until needed. It is placed where it serves a specific function. The stoplight loosejaw, a type of dragonfish, shows another version of this. Some dragonfishes can produce red light, a wavelength that many deep-sea animals cannot detect well. Red light disappears quickly in seawater from the surface. So many deep-sea animals have not retained the ability to see it. A predator that can produce and see red light gains something close to a private beam. It can illuminate prey without becoming obvious to that prey. Imagine the deep water as a room where most animals see only blue-green sparks. Then, one hunter carries a color of light that others do not recognize. The beam is not bright by human standards. It is not a spotlight cutting through a theater. It is small, controlled, close to the face. But to an animal with the right eyes, it can reveal a shrimp, a fish, or a red-bodied creature that would otherwise blend into darkness. This is not blindness in the simple sense. It is a world where different animals have different permissions. One animal cannot see what another can. One signal is public, another is private. A red body is camouflage to most observers, then suddenly exposed to a predator that has evolved the right lamp and the right retina. The midnight zone is dark, but it is not equally dark to everything. Dragonfishes, viperfishes, and related deep-sea predators often have long teeth, dark bodies, and photophores. Some are vertical migrators, rising toward shallower layers at night and descending again by day. Others remain deeper. Their prey may include small fishes, crustaceans, and squid. Their bodies are narrow and often dark enough to vanish outside the beam of a camera. The teeth can look excessive, but in a sparse habitat, holding prey once it is caught is critical. A surface predator may be able to chase another fish and try again after a miss. A deep predator may not get another chance soon. Teeth that prevent escape matter. A hinged jaw matters. A stomach that can stretch matters. A skull that opens widely matters. These features are not horror ornaments. They are ways of reducing the cost of uncertainty. The viperfish is often shown as a monster because its teeth are long enough to remain visible even when the mouth is closed. But a viperfish is not spending its life in a poster image. It is moving through cold water, waiting for smaller animals, managing energy, avoiding larger predators, and carrying its own lights in a world where the wrong glow can be fatal. Its frightening appearance is an artifact of survival under constraints. When these animals are brought to the surface in nets, they often look more extreme than they did alive. Pressure changes, damage, and handling can distort soft tissues. Mouths gape. Bodies collapse. Skin loses its living texture. A specimen in a jar is valuable, but it is not the whole animal. ROV footage has changed deep-sea biology, partly because it shows the body in the water that made it. In the water, a viperfish does not look like a fossilized nightmare. It is a fish hanging at an angle, drifting, waiting, adjusting its fins, watching for light or motion. Snow moves past it. Small animals pulse away from the camera. The predator does not need to own the darkness. It only needs to survive in it long enough for something edible to come near. This restraint is important. The deep sea is often described as if every animal there is an exception, every mouth a weapon, every eye a mutation, every body a mistake. But these are ordinary animals in their own environment. Their forms only seem extreme because the environment is extreme to us. The open water between 1,000 and 4,000 meters is one of the largest habitats on Earth. It has no forest, no grassland, no visible boundary, but it contains layers of animals moving through pressure, temperature, oxygen, and food gradients. Some animals migrate upward at night to feed in richer waters and return downward by day. Others feed on those migrants. Others wait for them to make mistakes. Vertical migration is one of the great daily movements of biomass on the planet. It happens mostly above the deepest parts of the midnight zone, but its effects descend. Animals that rise and fall carry carbon, nutrients, and risk between layers. Some become prey during migration. Some die and sink. Some release waste that falls. Even a hunter that never leaves the dark may depend on animals that do. A deep-sea food web is not a simple ladder from small to large. It is more like a moving web of falls, returns, flashes, bodies, and currents. A copod feeds near the surface. A lanternfish eats the copepod. A squid takes the lanternfish. A larger fish takes the squid. And eventually some part of that energy falls farther down. Nothing is wasted for long. Even bones and scales become habitat or food for someone. In the midnight zone, blindness can be a way of belonging to this web. A fish that waits in darkness does not need a bright world. A predator that detects smell does not need a horizon. A scavenger following chemical traces does not need to see the carcass from far away. The ocean carries the message before the body arrives. Smell is especially important where vision fails. Chemical signals move through water differently than light. They spread, distort, and thin out in currents, but they can lead animals toward food over distance. Deep-sea sharks, grenadiers, amphipods, hagfish, and many other scavengers respond to odor plumes from bait, carcasses, or injured animals. A whale fall can attract animals from surrounding depths, not because they see it, but because the water tells them something has changed. A baited camera on the seafloor may sit in darkness for a long time before the first animals arrive. Then a grenadier appears, following the scent. Amphipods gather. Hagfish move in with their pale bodies and probing mouths. Crabs and other scavengers may follow depending on depth and location. The scene can look sudden in edited footage, but the real process is chemical, gradual, and directional. Death in the deep sea is not an ending that belongs to one animal. It becomes a temporary concentration of energy in a place where food is usually diluted. A dead fish, a squid carcass, a whale body, or a jellyfall can change the behavior of every animal that can detect it. For scavengers and predators, blindness is less important when the whole current is carrying an invitation. But the title of hunter still applies carefully. A scavenger can also be a predator. A grenadier may feed on dead matter, small crustaceans, worms, or smaller fishes. A hagfish can enter carcasses and consume soft tissue, but also feed on weakened animals. The deep sea does not divide cleanly into noble hunters and low scavengers. It rewards flexibility. Many deep-sea animals are opportunistic because opportunity is the rule. Food arrives irregularly, and strict specialization can be costly. A predator may eat crustaceans when they are available, small fish when it can catch them, and carrion when it finds it. A mouth that looks designed for one dramatic act may in practice support a life of varied, uneven meals. This is one reason stomach contents are so valuable to scientists. Inside a preserved fish may be fragments of lanternfish, squid beaks, crustacean shells, or remains too digested to identify by shape alone. Each piece is evidence of feeding in a place where direct observation is rare. But stomach contents can also mislead if taken alone. They show what was eaten, not everything that was attempted, missed, or avoided. Modern tools are changing the picture. ROVs and submersibles bring cameras into deep water with lights, lasers, sampling arms, and suction devices. Baited landers wait without thrusters disturbing the water. Environmental data can reveal traces of animals that passed through without being filmed. Acoustic instruments can show layers of life moving in the water column. Museum specimens can be re-examined with CT scans and genetic tools. Even with these tools, the deep sea remains hard to know. The camera beam is narrow. The vehicle is loud and bright compared with the surrounding water. Animals may flee, freeze, approach, or behave differently. Nets collect what they can catch, and they damage soft bodies. The strongest evidence often comes from combining methods, not trusting one kind of observation alone. Think of the first living footage of a rare deep-sea anglerfish. Before cameras reached its depth, the animal was mostly known from dead or damaged specimens. Then the ROV light found a small black body alive in the water, its lure extended, its fins moving slightly, its whole existence no longer flattened into a drawing or a jar. That moment did not explain the entire species, it simply changed the quality of the question. A living animal carries context. It shows posture, buoyancy, movement, reaction, and scale against particles in the water. It shows that a fish with a terrible mouth can move delicately. It shows that a predator can be fragile. It shows that the deep sea is not only a place where strange bodies are found after death, but a place where those bodies make sense before we arrive. The word blind can also hide the violence of human light. When an ROV enters dark water, it brings lamps strong enough to reveal animals to us, but not necessarily neutral to them. Some deep sea eyes are extremely sensitive. Sudden illumination may startle or disorient animals. Some organisms are attracted to lights, others avoid them. The record we get is shaped by the act of recording. This means that the hunter we observe may not be behaving as it was moments earlier. A fish facing into the current may turn away. A shrimp may freeze. A squid may darken or flash. A predator might miss prey because the vehicle has altered the scene. The deep ocean is not a stage waiting for us. It is an environment interrupted briefly by our instruments. Still, the instruments reveal patterns. They show tripod fish standing in currents. They show anglerfish lures. They show dragonfish and viperfish suspended in the water column. They show animals using red, black, transparent, silver, and blue-green strategies. They show that the loss or reduction of ordinary vision is not a single evolutionary path, but one of many responses to darkness. Some animals enlarge their eyes in the twilight zone, where faint sunlight remains and silhouettes can still matter. Others reduce eyes deeper down. Some maintain visual systems tuned to bioluminescent points. Some abandon image formation almost entirely. Depth is not one condition. It is a gradient, and along that gradient, eyes change according to what information is worth keeping. At around 200 meters, much of the red light from the surface has already disappeared. This is why red animals can look dark at depth. By the time the ocean reaches the bathypelagic zone, sunlight is no longer part of the visual world, but bioluminescent light remains. Most biological light in the sea is blue-green, because those wavelengths travel best through seawater. A predator that sees blue-green flashes can detect events. A predator that produces red light can create a more private search tool. This physics shapes color. Black skin absorbs stray light and hides a body against darkness. Red skin can appear black, where red light is absent. Silver sides may reflect the dim environment in shallower layers. Transparency can make small animals difficult to see in mid-water. Counter-illumination can break the silhouette of an animal seen from below. There is no one way to disappear. In a shallow coral reef, camouflage is often about matching a background. In the midnight zone, there may be no background at all. There is only water, faint light from living things, and the angles from which another animal might detect you. To hide, a body must manage contrast, reflection, glow, motion, and the pressure wave it leaves behind. For a blind or near-blind hunter, prey may be detected first not as an image, but as a failure of the water to remain still. A tiny animal beating its swimming legs creates turbulence. A fishtail produces pulses. A squid jet leaves a sudden disturbance. These signals fade quickly, but a predator close enough to sense them can react. The tripod fish uses touch at the edge of contact. Anglerfish use light at the edge of attention. Dragonfish use vision at the edge of what other animals can see. Grenadiers and hagfish use smell at the edge of a chemical plume. The phrase blind hunter gathers all these strategies under one title, but the reality is a set of different solutions to the same absence. And the absence is not only light, it is also distance. The ocean is enormous in 3 dimensions. A predator may be only meters from prey and still never encounter it. A mate may be nearby by human standards and impossibly far by chemical or visual standards. In open water, there are no trails, no dens, no trees, no corners. The animal must create a life in a moving void that is not empty, but rarely generous. This is why deep-sea hunters often look patient. Patience is not a personality here. It is physics translated into behavior. Moving fast through cold, dark, food-poor water can burn energy faster than it can be replaced. A predator that waits may outlive a predator that chases. A mouth that opens quickly after hours of stillness may be more successful than a body built for constant pursuit. The anglerfish lure is one form of patience. The tripod stance is another. A gulper eel drifting with an enormous mouth is another. A jellyfish with trailing tentacles is another, although not a fish and not blind in the same way. Across the deep ocean, long lines, traps, passive contact, and sudden closure repeat again and again. The pelican eel, or gulper eel, is often described by its enormous mouth, but the mouth alone does not explain the animal. It has a long, slender body and a jaw that can open widely, allowing it to take prey that may be large relative to its own body. Its eyes are small. Its body is dark. It lives in deep water, where encounters with prey are uncertain. The oversized mouth increases the range of what can be accepted when food appears. This does not mean the pelican eel is swallowing everything in its path. The deep sea is full of myths created from anatomy. A large mouth becomes a story about constant devouring, but a large mouth in a sparse habitat may be more about flexibility than appetite. It is a way of making a rare encounter count. The same caution applies to fangtooths, black swallowers, and other deep-sea fishes with dramatic jaws or expandable stomachs. Their anatomy suggests they can handle relatively large prey, and stomach contents sometimes confirm surprising meals. But maximum capacity is not daily life. A predator that can swallow a large fish does not necessarily do it often. Extreme events preserve well in stories because they are extreme. Most of the time, the animal is simply living. It moves, waits, senses, digests, avoids danger, and tries to reproduce. The drama is real, but it is not constant. The deep ocean is not a battlefield with monsters colliding in every frame. It is a habitat where survival may depend on long intervals between visible events. A camera lowered into black water may record 10 minutes of nothing but snow, and that nothing is not empty. It is the normal pace of the place. Human attention wants a body to enter the frame. The animals do not owe the camera a scene. Their lives continue in darkness beyond the light, in distances the vehicle will never cross. When a hunter finally appears, it is tempting to treat the moment as an arrival from nowhere. But the animal was already there, integrated into currents, prey fields, temperature, oxygen, and pressure. The machine did not discover a monster. It crossed paths with a resident. Oxygen also shapes deep-sea hunting. In some regions, oxygen minimum zones form where the supply of oxygen is low. Animals living near or within these layers may have adaptations that allow them to tolerate low oxygen or reduce their metabolic demands. Predators may use the edges of these layers because prey can concentrate there, or because some species are more vulnerable when moving between oxygen conditions. The ocean is layered not only by light, but by chemistry. A fish descending from the twilight zone into deeper water experiences changes in oxygen, temperature, pressure, and food availability. A predator positioned at the right depth may take advantage of animals crossing these boundaries. The hunter does not need a map. Its body, senses, and behavior are the map. Seamounts complicate the midnight zone in another way. These underwater mountains rise from the seafloor, sometimes reaching into the bathypelagic or mesopelagic layers. Currents strike them, accelerate, swirl, and lift nutrients. Animals gather around them. Predators follow. A dark slope that no human sees from the surface can become a concentration point for life across thousands of meters of water. A seamount is not a reef in the tropical postcard sense, but it can function as an island of structure. Corals and sponges may grow on hard surfaces. Fishes hover near the slopes. Squid, sharks, and larger predators may move through the area. For blind or low-light hunters, the currents around seamounts can bring prey within reach, just as currents across the abyssal seafloor bring food to a tripod fish. Continental slopes are also important. They are the long descending margins where continents fall toward the deep ocean basin. Submarine canyons cut through them, sometimes carrying organic material from shallower water into depth. These canyons can be busy compared with the surrounding deep seafloor. They are places where sediment moves, carcasses collect, and animals concentrate along walls and channels. A blind hunter on a slope may not need to travel across featureless plains. It can use terrain. It can face into water moving along the canyon. It can search the sediment with barbels or fins. It can follow odor downstream or upstream depending on the signal. The darkness remains, but the environment gives direction. Direction is one of the most valuable things in the deep sea. A faint chemical trail, a current line, a flash, a vibration, a touch on a fin ray. Each one says that the world is not uniform. Each one reduces the impossible size of the ocean into a path an animal can take. Humans often imagine blindness as a closing down of the world. For many animals, it is not that simple. A blind cavefish, a deep-sea tripod fish, a hagfish following scent, a shark reading electric fields. Each lives in a world full of signals that humans are poor at imagining. The loss of one sense can reveal the importance of others. The lateral line is not magic. It works only over certain distances, and signals degrade in turbulence. Smell can be powerful, but currents twist odor plumes into broken ribbons. Touch requires closeness. Bioluminescent lures can attract, but they can also fail or attract the wrong animal. Every sensory strategy has limits. This is why deep-sea hunting is a balance of systems. An animal may use smell to orient broadly, lateral line to detect movement nearby, touch to confirm contact, and vision to notice bioluminescent flashes. Even animals with reduced eyes are not sensing with one replacement sense. They are combining fragments of information under conditions where no fragment is complete. Direct experiments in the midnight zone are difficult. Scientists can study anatomy in the lab, measure light sensitivity in specimens, analyze genes, compare eye structure, and observe behavior in rare footage. But following one individual through weeks of hunting in darkness is still beyond ordinary reach. The deep sea resists continuous observation. So the story must remain cautious. We can say a tripod fish waits on modified fins and uses sensitive feelers. We can say many anglerfishes use bioluminescent lures. We can say dragonfishes include species with red bioluminescence. We can say deep sea fishes show specializations of eyes, lateral lines, smell, and body form. We should not pretend to know every decision those animals make in darkness. The unknown is not a gap to fill with monsters. It is part of the habitat. When a camera sees an anglerfish for 30 seconds, that is not a complete biography. When a trawl brings up a fish with a swallowed prey item, that is not a full feeding history. When a DNA trace appears in a water sample, that is not a sighting. Each record is a footprint, not the whole animal, but enough footprints can show direction. Across the midnight zone, hunting without ordinary sight is not rare. It is one of the basic ways life continues after sunlight ends. The midnight zone also contains animals with eyes that are not reduced, but highly specialized. Some deep sea fishes have tubular eyes pointed upward, adapted to detect silhouettes or faint light from above in the twilight zone and upper darkness. Some have retinas tuned to blue-green bioluminescence. Some have optical sensitivity far beyond a human eye in dim light. Blindness, again, is not a universal rule. It is part of a broader pattern of sensory trade-offs. The deeper the animal lives, the less useful sunlight becomes. But depth alone does not determine everything. A fish near the seafloor may have different visual needs from one in open water. A predator near vents or seeps may encounter light produced by organisms, but also chemical gradients, heat, and dense communities. A midwater ambush predator may care most about flashes. A benthic hunter may care most about touch and smell. Hydrothermal vents are often discussed for their chemistry rather than their predators, but they also belong to the dark ocean. Around vent fields, life is organized not by falling sunlight energy alone, but by chemical energy from the earth. Bacteria and archaea use reduced chemicals from vent fluids, and animals build communities around that production. Predators and scavengers enter these systems, feeding among shrimp, crabs, worms, and fish. Vent animals are not the main subject of the midnight zone as a whole, because vents are local and unusual. But they show something important. Darkness does not mean one kind of ecosystem. In some places, the deep sea is sparse and slow. In others, chemical energy creates dense life around black smoker chimneys or shimmering fluids. A blind hunter near a vent is reading a crowded darkness, not an empty one. Cold seeps create another kind of deep habitat. Methane, sulfide, and other chemicals seep from the seafloor, supporting microbial life and communities of clams, mussels, worms, and other organisms. These systems can last far longer than whale falls and differ from hydrothermal vents in temperature and chemistry. They become patches of food and structure in deep water. A predator moving through a seep does not need sunlight to find abundance. It can follow chemical signals, animal movement, current patterns, and the edge between seep community and ordinary sediment. The darkness is the same darkness, but the rules of food are different. Whale falls are more temporary, but they are among the clearest examples of how a single body can transform the deep. When a whale dies and sinks, it carries tons of organic material from the surface into the deep sea. Scavengers strip soft tissue. Worms and microbes work the bones. Chemical processes create stages of life that can last years. Blind and low-light feeders may arrive because of smell long before a human camera records the skeleton. A whale fall is not a peaceful monument. It is feeding, competition, reproduction, decomposition, and chemical change. Hagfish twist into flesh. Sharks and large fishes may remove tissue. Amphipods swarm. Later, bone-eating worms and bacterial mats alter what remains. The carcass becomes habitat because in the deep sea, food and place can become the same thing. Imagine an ROV descending to a whale skeleton on the seafloor. The bones are pale in the lights. The sediment around them is disturbed. Small animals move across rib surfaces. A hagfish passes through a gap. There is no sunlight, no reef color, no waves overhead. Yet the scene is crowded with consequence. A life that began at the surface is still feeding animals in darkness. For blind hunters, such places matter because they gather prey. Scavengers attract predators. Disturbed sediment exposes worms. Chemical signals bring animals from beyond the camera frame. The first animal to detect the fall may not see it at all. It may smell it as a widening difference in the water. Smell in water is not like smell in air. A plume can be stretched into filaments by current. An animal following it may move in a pattern, turning when the signal strengthens or weakens, correcting its path as the chemical information breaks apart. This is one reason baited lander footage often shows animals approaching from downstream positions. They are not randomly wandering into the frame, they are solving a chemical problem. The same principle can guide active predators toward living prey. A wounded squid, a stressed crustacean, or a dense patch of smaller animals may release chemical cues. These cues are not always enough for capture, but they reduce the search. In a habitat where search is expensive, any reduction matters. Some deep sea fishes have barbels, chin organs, or elongated fin rays that increase the reach of touch and chemosensory detection. These structures can sweep sediment, sample water, or detect small animals nearby. They may look decorative in photographs, but they are often functional extensions of the sensory body. The animal becomes larger than its core outline because its sensing field extends beyond its skin. In darkness, this matters. A hunter with long rays or barbels can encounter prey before the mouth does. It can feel the ground without placing the head directly into sediment. It can detect drifting animals before they pass out of reach. The body becomes a net of information. There is a quiet elegance in that. Not elegance in the human sense of beauty, but in the economy of a solution. A fish standing still with long feelers is not less advanced than a fast predator with sharp eyes. It is adapted to a different equation. The deep sea does not reward the same body plans the surface rewards. The same can be said of slow movement. A deep sea fish hovering almost motionless may look inactive, but inactivity can be a strategy. It reduces energy cost, reduces hydrodynamic noise, and may prevent detection by prey or predators. In darkness, the animal that disturbs the water least may have the advantage. But no hunter is safe. A blind predator is also prey for something else. Larger fishes, squid, sharks, and marine mammals enter or exploit deep layers. Sperm whales dive into darkness to hunt squid. Deep-diving beaked whales follow prey into zones where humans cannot easily watch them. Large squids hunt fish and are hunted in turn. Teeth, beaks, scars, and stomach contents show that the darkness contains many directions of danger. A viperfish may be a predator of small fishes and crustaceans, but it can also be swallowed. An anglerfish may lure prey, but it can be taken by a larger animal. A tripod fish may wait above sediment, but a passing predator can end that waiting instantly. The deep sea has no final monster at the top of every chain. It has overlapping risks. Even the largest deep-diving predators are known partly through indirect evidence. Sperm whales surface with sucker scars. Squid beaks are found in stomach contents. Acoustic tags reveal dives. Rare footage shows encounters, but most events happen unseen. The deep sea is full of interactions that leave marks rather than recordings. This is why a script about blind hunters must include the evidence, not just the animals. Without evidence, the darkness becomes a canvas for invention. With evidence, it becomes stranger and more grounded at the same time. A preserved specimen in a museum jar may carry more information than it first appears. Its eye size can be measured. Its teeth can be examined. Its stomach can be opened. Its otoliths, the small earstones of fishes, can reveal growth information. Its DNA can clarify relationships. Its skin and photophores can be compared with related species. A body taken from the deep is not only an object of curiosity, it is a record. But it is also an incomplete record. The animal may have been damaged in a trawl. The pressure change may have altered tissues. The colors may fade in preservative. The posture is lost. The behavior is absent. A jar can preserve anatomy, not context. This is where ROV footage and specimens meet. The camera shows the animal in place, but may not collect it. The specimen allows close study, but removes the animal from place. Together, they give a more complete picture. A tripod fish filmed standing on its fin rays makes the modified anatomy understandable. An anglerfish specimen explains the lure in detail, but living footage shows how quietly it carries it. The deep sea has always required this kind of assembling. A bone from one expedition, a video from another, a DNA sequence from a water sample, a stomach content analysis from a trawl, a depth record from a tagged animal. Knowledge arrives the way food arrives, in fragments, from above, across distance, and after long waiting. In the control room of a research vessel, the deep ocean appears as a monitor surrounded by people, cables, maps, and instrument readouts. The room may be dark, so the screen is easier to see. Outside, the ship moves on a surface that looks ordinary. Below, the ROV is thousands of meters down, and every image travels back through a tether thinner than the distance makes it feel. A scientist may call out a depth, another may mark the time. Someone may identify a fish, or say they are not sure. The manipulator arm may stay folded because the animal is too delicate or too far away. The pilot may hold position in a current. For a few minutes, a blind hunter becomes visible to human knowledge. Then it disappears. It does not vanish into mystery because mystery wanted it back. It swims or drifts beyond the lamps, returning to conditions that existed before the vehicle arrived. The data remain. The animal continues if it has not been disturbed too much. This is often the best outcome: a record without capture, an encounter without possession. The deep sea teaches restraint because it punishes overconfidence. A single observation can be important, but it rarely closes the question. One fish at one depth in one canyon is not the whole species. One feeding event is not a complete diet. One lure movement is not a full behavioral repertoire. The midnight zone is not uniformly populated. In some areas, the water column may be sparse. In others, layers of prey are denser. Productivity at the surface affects what falls. Upwelling, seasonal blooms, oxygen, currents, and seafloor topography all shape deep life. A hunter in the North Pacific does not necessarily live under the same conditions as a related hunter in the Atlantic or Southern Ocean. This geographic variation matters because adaptations are always local as well as general. Darkness is shared, but food supply, temperature, current, oxygen, and prey communities differ. A species may be widespread, but still encounter different conditions across its range. Scientists must be careful when turning one region into a global rule. The term midnight zone itself is a simplification. It helps humans divide the ocean into layers, but animals do not stop at our definitions. Some move across boundaries, some live near the top of the bathypelagic and interact with twilight zone migrants. Some live near the bottom of it and connect to abyssal systems. Some use canyons or slopes that cut across depth categories. The lines are useful, but life crosses them. The title, then, is less about a strict layer than about a condition, Hunting after ordinary light has ended. That condition begins around the loss of sunlight and deepens with distance from the surface. It includes fish with reduced eyes, predators with specialized vision, scavengers following scent, and animals using touch in water so dark that a human eye would have no scene to build. The human eye is a poor instrument for imagining this. We think darkness means absence because our visual world collapses without light. But water is not empty of signals when it is dark. It is full of pressure, sound, chemicals, motion, temperature, and the brief lights of living bodies. To call the hunters blind is to describe them from our weakness as much as from theirs. A tripod fish does not need to know the color of a crustacean. It needs to know that something has touched the sensitive rays ahead of its mouth. An anglerfish does not need to scan a reef. It needs a small animal to make one fatal decision near a lure. A dragonfish does not need daylight. It needs control over the kind of light others cannot use. There are deep-sea crustaceans that move through this darkness with long antennae, tasting and touching the world. There are cephalopods with eyes adapted to faint signals, arms ready to gather prey in close range. There are jelly predators whose tentacles create drifting traps. There are worms that wait in sediment and animals that bury themselves until a signal passes overhead. Not all of them fit the word hunter in the same way. Some are filter feeders. Some are scavengers. Some are ambush predators. Some are parasites. But the sensory theme continues. When light disappears, bodies become instruments for reading water. In fishes, the inner ear can detect sound and acceleration. The lateral line can detect water motion. Chemoreception can detect dissolved substances. Taste can be distributed around the mouth or body. Vision may remain useful for bioluminescence. Electroreception is important in sharks, rays, and some other fishes, though not universal across deep-sea predators. Each sense has a range, and the ranges overlap. The hunter is not only its mouth, it is the entire sensory surface. A large head may hold olfactory organs. Long fins may extend detection. Skin may reduce reflection. Photophores may manage light. Teeth may retain prey. Stomach and metabolism may handle long gaps. Every part participates in the ecology of darkness. The prey has its own adaptations. Many small animals are transparent, silvered, dark red, or counter-illuminated. Some flash to startle predators. Some release glowing fluid. Some migrate to avoid the worst risk at any one depth. Some reduce movement. Some form layers. Some are armed with spines. A blind hunter is entering an arms race, where prey is also shaped by darkness. A glowing lure may attract one animal and frighten another. A pressure wave may reveal prey, but the predator's own motion may reveal it in return. A chemical trail can lead a hunter to food, but the same trail can attract competitors. The deep sea is not a place of perfect adaptations. It is a place of trade-offs. Evolution does not plan these trade-offs. It filters variation through survival and reproduction. An eye becomes smaller if smaller eyes do not reduce success and save energy or tissue. A fin ray becomes longer if longer rays improve feeding or sensing enough to matter. A lure persists if animals with lures leave more offspring. The result can look designed, but it is history shaped by selection. This makes the animals more impressive, not less. Their bodies are not inventions created for our astonishment. They are accumulated answers to pressures that have operated in darkness over immense spans of time. The deep sea is old as a habitat, but its animals are not unchanged relics. They have evolved, diversified, disappeared, and been replaced. The darkness may seem timeless from a human point of view, yet the communities within it respond to climate, food supply, oxygen, geological change, and extinction. The midnight zone has history, even when it leaves fewer obvious fossils than shallow seas. Soft bodies do not always preserve well. Many midwater animals leave little in the fossil record. The history of a lure, a photophore, or a sensory canal may have to be reconstructed from living species, genetics, and rare fossils. The deep ocean hides its past almost as effectively as it hides its present. Sometimes the evidence comes ashore in a form that feels out of place. A deep-sea anglerfish on a beach. A strange black fish found by a walker. A squid body floating at the surface. A predator from pressure and darkness lying under gulls and daylight. These events attract attention because they break the boundary between worlds. But a stranded deep-sea animal is usually a damaged messenger. It may be sick, dead, displaced, or changed by its ascent. It can still teach scientists, but it should not be mistaken for the animal's normal life. The beach is not where the story happened. It is where one piece of the story became visible. Museum collections are full of such pieces. Some were collected by trawls, some by expeditions, some by strandings, some by fisheries. Labels record locations, depths, dates, and collectors. A jar may sit quietly for decades before new methods make it valuable again. NOAA can be extracted. Structures can be scanned. Old specimens can answer questions the original collectors did not know to ask. Deep-sea science often works this way. It depends on patience across generations. One expedition gathers animals. Another revises their classification. Another films a related species alive. Another studies its sensory organs. The understanding grows slowly, like a map drawn from scattered soundings. For blind hunters, anatomy is especially important because behavior is hard to watch. Eye size, retinal structure, olfactory organs, lateral line canals, fin rays, jaw mechanics, stomach capacity, photophore placement, and skin color all suggest how an animal interacts with darkness. But anatomy must be interpreted carefully. A structure can have more than one use. A feature that looks predatory may also be used in mating or defense. Bioluminescence is a good example. A light organ may attract prey, signal mates, camouflage a silhouette, startle predators, or confuse attackers. In some animals, the function may change with context. A glow is not automatically a lure. A flash is not automatically a warning. The meaning depends on the animal, the depth, the direction, and the observer. The living light of the deep sea is sometimes compared to stars, but that comparison can mislead. Stars are far away and indifferent. Bioluminescent points are close, biological, and risky. They are made by bodies under pressure. They turn on and off because something is happening. A flash may be the last signal a prey animal gives before being eaten, or the signal that prevents it from being eaten. To a blind or low-vision hunter, a flash may be enough. Not enough to see the animal in detail, but enough to orient, close distance, and prepare the mouth. The exact shape of prey may matter less than its position and movement. A point of light becomes a location. In the darkness, location is everything. A predator cannot eat an animal it cannot reach. It cannot mate with an animal it cannot find. It cannot avoid a threat it cannot detect. Every adaptation in the midnight zone is partly an answer to the question of where. Where is food? Where is danger? Where is current? Where is the bottom? Where is another body? For humans, location is measured with GPS, sonar, depth sensors, maps, and coordinates. For the animal, it is measured in gradients, vibrations, pressure, and signals that change across the skin. The deep-sea hunter lives inside a map that is constantly moving. Sound also travels well underwater, though its role varies among deep-sea animals and is not always easy to study. Fishes can detect particle motion and pressure changes through inner ear structures, and some may use sound to locate events or communicate. In a dark habitat, acoustic information may be important, but it is hard to assign specific behaviors without direct evidence. The caution matters. It is easy to give every blind animal extraordinary powers. The truth is more interesting because it is limited. Senses have thresholds. Signals decay. Noise interferes. A hunter succeeds not because it knows everything, but because it knows enough at the right moment. Enough is the deep sea's central word. Enough food to last, enough light to locate, enough scent to orient, enough motion to strike, enough energy to wait, enough luck to meet a mate. The animals here are not built for excess. They are built around margins. A surface reef can look abundant to the point of distraction. Fish dart everywhere. Colors compete. Coral structure creates endless hiding places. The midnight zone removes that visual abundance. It forces attention towards small events, because small events may be the only ones that matter for a long time. Yet across the scale of the whole ocean, those small events add up to enormous life. A single camera frame may show almost nothing, but the volume of deep water is vast. A sparse density of animals spread through such volume can still represent a major part of the planet's living system. The darkness looks empty because the human field of view is tiny. This is another form of blindness, our own. We send a camera into a few meters of light and try to understand a habitat measured in millions of cubic kilometers. We see a fish and call it rare because we rarely see it. Sometimes it is truly rare. Sometimes our access is rare. Scientists try to correct for this with repeated surveys, acoustic measurements, nets, genetic sampling, and long-term observatories. Each method has bias. Nets miss fragile animals or destroy them. Cameras may attract or repel. Acoustics detect layers, but not every species. DNA can show presence without abundance. A cautious picture emerges from overlap. The blind hunters of the midnight zone are therefore not just a group of animals. They are also a lesson in how knowledge is built under difficult conditions. We learn from what appears, from what is caught, from what is left in stomachs, from what glows, from what does not glow, from what survives the journey to the surface, and from what never does. In some footage, a deep sea fish holds still while the rove approaches. It may be stunned by the light, or simply using stillness as it always does. Particles drift between the animal and the lens. The pilot holds position. For a few seconds, every viewer becomes dependent on the same thing the animal does, small signals in darkness. Then, the fish moves. Not quickly, perhaps not dramatically. A tail beat, a turn, a fade into black. The camera follows for a moment and loses it. The screen returns to snow. The absence after the animal leaves feels larger because now we know what it contained. The midnight zone also interacts with human systems in ways that are no longer distant. Deep sea fisheries have targeted some slow-growing species on slopes and seamounts. Plastic debris and microplastics can reach deep waters. Climate change can alter surface productivity, oxygen distribution, and the amount or timing of food sinking into depth. Proposed deep-sea mining raises concerns about habitats that recover slowly, if they recover at all. These issues should not be forced into every animal story, but they are part of the real habitat now. A blind hunter is not protected from human influence simply because it lives beyond sunlight. The surface and the deep are connected by carbon, water, particles, currents, and increasingly by human waste and industry. The tragedy of deep sea damage is that it can occur before the life there is well known. A seamount trawled for fish may lose coral structures that took centuries to grow. A mining plume could spread through habitats where animals depend on thin layers of sediment and chemical stability. A change in surface plankton could alter the food supply far below. Darkness does not make ecosystems invulnerable. At the same time, fear should not become the only way we talk about the deep. Protection depends on understanding, and understanding requires seeing these animals as part of functioning systems rather than as curiosities. A tripod fish is not a symbol. An anglerfish is not a nightmare. A dragonfish is not a villain. They are residents of a world connected to ours whether we notice it or not. The more we learn, the less empty the darkness becomes. Not brighter, exactly, but more legible. A point of light becomes a lure or a warning. A long fin ray becomes a sensor. A small eye becomes a trade-off. A jaw becomes a solution to scarcity. A body in a jar becomes one page in a much larger record. And still, much remains unobserved. There are hunts that will never be filmed. Migrations that pass under ships without being resolved into species. Chemical trails followed in darkness with no witness. Prey swallowed beyond the camera beam. Mates found after distances we do not know how to imagine. The RUV continues downward, and the depth number changes on the screen. The water outside does not look different in a simple way. It is still black, still full of particles, still cold, but the pressure increases, the surface recedes, and the animals that appear belong more completely to a world where ordinary sight is optional. A fish with reduced eyes crosses the frame. It turns not toward the light, but into the current. Its fins hold the body steady. A thread-like ray touches the water ahead. Nothing happens for several seconds. Then, the head flicks, the mouth opens, and something too small for the camera to follow disappears. That is what hunting can look like here. No chase across a blue ocean, no burst through a bait ball, no dramatic surface splash, just a body aligned with invisible flow, a signal detected at close range, and a brief motion that decides whether energy continues into one animal or another. The simplicity is deceptive. Behind that moment are millions of years of adaptation, the physics of light absorption, the chemistry of scent, the mechanics of fin rays, the ecology of marine snow, the pressure of scarcity, and the need to survive long enough for the next event. Blindness in this context is not a single condition. It includes animals with no useful eyes, animals with reduced eyes, animals that prioritize other senses, and animals whose vision is tuned to signals humans barely perceive. It includes seafloor ambush predators and midwater lure bearers. It includes scavengers that follow odor and hunters that detect vibrations. It includes species we know well enough to describe, and species known from only a handful of records. The term is useful because it points toward a truth. The midnight zone cannot be understood through daylight assumptions. Eyes are only one way to know the world. In deep water, the body becomes a more distributed instrument, and hunting becomes a negotiation with signals that are faint, broken, and brief. Consider again the tripod fish. It is one of the most literal blind hunters of the deep seafloor. Its eyes are reduced, its body raised on fin rays, its pectoral feelers spread into the current. It does not appear powerful in a conventional sense. It does not need to be. Its power is positional. It lets water do part of the searching. The animal's stillness can last long enough that sediment settles around the base of the rays. Particles pass. Small crustaceans drift in and out of reach. The fish waits at the height where prey is most likely to pass. It is a trap made of posture. This kind of ambush is common in environments where movement is costly. On land, a spider web can capture flying insects with little active pursuit. In shallow water, a frogfish can wait on a reef and strike when prey comes close. In the deep sea, a tripod fish uses current and touch. The principle is similar, but the materials are different. There is no web, no coral head, no daylight. There is only body, water, and timing. The sensory feelers of the tripod fish do not have to identify prey in the way a human identifies an object. They must distinguish meaningful contact from background flow. They must trigger the animal at the right time. Too sensitive, and the fish wastes energy. Not sensitive enough, and meals pass unnoticed. Evolution tunes the threshold. Researchers can describe the anatomy and observe the behavior, but many details remain uncertain. How often does the fish feed? Which prey are most important at different depths? How far can its sensory rays detect motion rather than direct contact? How does current speed affect posture? These are not trivial questions. They are the difference between a striking image and a full ecological understanding. Still, the image is important because it gives a form to a concept. A blind hunter does not have to wander helplessly. It can turn a current into a hunting lane. Now consider the anglerfish again, alone in open black water. It has no seafloor under it, no current lane it can stand inside, no wall to guide prey. Instead, it carries a signal. The lure is a small island of attention in a large darkness. The mouth waits behind it. The prey that approaches may be curious, hungry, confused, or simply following a response shaped by many generations of deep sea life. The exact mental state does not matter. The geometry matters. Light, approach, mouth. In a place where finding prey is difficult, the anglerfish changes the problem by making prey participate in the encounter. But the lure does not guarantee a meal. Prey may turn away, another predator may notice. The anglerfish may spend long intervals without success. Its own body must stay alive while doing very little. This is the less sensational part of ambush predation. Waiting is not passive when waiting is the main energetic strategy. The animal must maintain buoyancy, tissues, bacterial symbionts, sensory awareness, and reproductive readiness across long periods of scarcity. Its fearsome mouth is only the visible end of a much quieter system. Deep-sea anglerfishes belong to a diverse group, and not every species has the same lure shape, depth range, or reproductive strategy. Some lures are simple, others are elaborate, branched, or fringed. Some species have additional luminous structures. Some are known from only a limited number of specimens. Taxonomy continues to change as researchers examine morphology and genetics. This diversity matters because the popular image of one anglerfish often stands in for all of them. The real group is broader and stranger in a less simple way. There is no single anglerfish lifestyle, only variations on feeding, mating, and surviving in dark water. The dragonfish offers a different lesson. It is not blind in the ordinary sense. It may have functional eyes and active predatory behavior, but it hunts among animals that cannot see everything it can. Its red light changes the sensory field. It creates asymmetry. The prey is effectively blind to one part of the predator's world. This reminds us that blindness can be relational. An animal may be blind to red, but not blue. Blind to chemical traces, but sensitive to vibration. Blind to a still body, but responsive to movement. In the midnight zone, what matters is not whether light exists, but who can use it. Most bioluminescence in the ocean is produced through chemical reactions involving light-emitting molecules and enzymes or bacterial symbionts, depending on the organism. The details vary widely. Some animals make their own light. Some host bacteria that produce it. Some control the exposure of light organs with shutters, pigments, or movements. The result is a biological signal that can be turned into camouflage, communication, defense, or predation. For hunters, light is especially dangerous because it reveals the source. A lure must place brightness away from the vulnerable body, or near the mouth where the risk becomes useful. A searchlight must be dim or private enough not to advertise too widely. Counter-illumination must match the faint light from above, or it creates a silhouette instead of hiding one. Every light in the deep sea is a wager. Turn it on, and something may come closer. Turn it on and something else may find you. Stay dark, and prey may pass unseen. Stay dark, and you may live longer. The animals of the midnight zone do not solve darkness once. They negotiate it repeatedly. This is why many deep-sea predators are black. Not black as a symbol, but black as an optical strategy. Dark skin absorbs stray bioluminescent light, reducing reflection. In a world where even a faint outline can matter, absorbing light can be protection. Ultra-dark surfaces in some deep-sea fishes make them difficult to illuminate even under research lights. To human eyes, black animals in black water seem to disappear into absence, but to another deep-sea animal, the question is finer. Does the body reflect a flash? Does it interrupt a glow? Does it move water? Does it smell? Does it make pressure? Disappearance is never complete. It is always disappearance from someone. The hunter and the hunted are both trying to manage detection. The prey reduces its signal. The predator increases sensitivity. The prey releases light to confuse. The predator learns which signals matter. Neither side wins permanently. The arms race is not always direct. A feature that begins as defense may later be used for communication. A light used to startle predators may also attract mates. A dark body that hides from predators also helps a predator approach prey. Evolution works with what exists, and functions can overlap. This is why scientists avoid overly simple stories when possible. A photophore is not just a lamp. A tooth is not just a weapon. A reduced eye is not just a loss. Each feature sits inside behavior, ecology, development, and history. In the museum, these features are still. In the ocean, they move. A lure sways. A fin ray bends. A jaw opens. A photophore brightens or dims. A body rotates in current. A fish that seemed like a preserved oddity becomes a sequence of decisions. This change from object to animal is one of the deepest shifts in modern ocean exploration. Cameras do not replace specimens, but they return motion to anatomy. They show that even the strangest body is part of ordinary behavior somewhere. The midnight zone also contains cephalopods, including squids and octopods adapted to deep water. Some have large eyes because they detect faint light or silhouettes. Others use arms, suckers, skin patterns, and bioluminescent structures in ways that are still not fully understood. They are predators, prey, and competitors in the same dark systems as deep-sea fishes. A squid in the midnight zone may detect a fish before the fish detects it, or may be detected by a whale, a shark, or a larger squid. Its arms can seize prey at close range. Its body can jet away. Its tissues may be soft and difficult to preserve. Much of its life may be known from beaks found in stomachs, rare footage, or damaged specimens. Cephalopod beaks are small, hard records of animals that otherwise vanish quickly. In the stomach of a sperm whale, they can accumulate and reveal what has been eaten. On the seafloor or in sediment, they may persist after soft tissues are gone. A beak is not dramatic by itself, but it can point toward a hunt that happened in darkness without witnesses. Sucker marks on whale skin tell another kind of story. They do not show the whole encounter, but they show contact between bodies at depth. A whale dives. A squid resists. Skin records the pressure of arms. The animal surfaces carrying marks from a fight that took place beyond sunlight. These traces remind us that blindness does not mean stillness. Some deep hunts are fast, forceful, and large, but even then, they are hard to see directly. A whale's dive can be tracked. A squid can be inferred. A scar can be measured. The actual moment, the collision in darkness, may remain outside human observation. The deep sea is full of such almost known events. Enough evidence to know they happen, not enough to watch them fully. That tension is part of its realism. Technology keeps narrowing the gap. Animal-borne cameras have begun to show behaviors from the perspective of large marine animals. Deep-sea observatories can monitor one place over time. Autonomous vehicles can survey without a tether. Low-light cameras and red illumination can reduce disturbance in some settings. Genetic tools can identify prey remains that are too digested for visual identification. But technology does not remove the deep ocean's scale. It extends a few senses into it. A camera is still a small window. A tag is still one animal. A net is still one path through water. The ocean remains larger than the method. This is not a reason for despair. It is a reason for humility. The animals of the midnight zone have always lived beyond complete observation. Science approaches them through patience, repetition, and careful inference. The unknown is not defeated all at once. It is reduced in small, reliable ways. A blind hunter crossing a camera beam becomes one of those reductions. A little less unknown, not captured by myth, not fully explained. Seen enough to become part of a better question. Among the smallest and most numerous prey of deep predators are crustaceans, copepods, amphipods, ostracods, krill-like animals, and shrimps, depending on depth and region. Many produce light or respond quickly to disturbance. They graze, scavenge, migrate, and become food for fishes and cephalopods. Without them, many larger predators would have little to catch. The deep sea is often described through its large, strange animals, but much of its energy passes through small bodies. A blind hunter may depend not on dramatic prey, but on tiny animals delivered by current or migration. The mouth closes on a brief flicker of life, and that is enough. This changes the way a camera scene should be read. A fish alone in the frame is not alone in the ecosystem. Around it are animals too small, too dim, too fast, or too far from the lens to notice. The predator's stillness is aimed at a world below our visual threshold. A human viewer may see emptiness because the prey are not obvious. The fish may sense a moving field of possible meals. Its blindness to images may be accompanied by a sensitivity to events the camera does not capture. Snow falls. A fish waits. A small crustacean passes. The mouth opens. The snow continues. There is no music in the water, no narration, no cut to another angle. The event is finished before the viewer has fully understood it. This is why the deep sea can feel slow and sudden at the same time. Long waiting, quick contact. Long darkness, brief light. Long hunger, brief feeding. The rhythm is not cinematic by design, but it becomes cinematic because it is so different from the pace of surface life. The danger of making a film about these animals is turning that rhythm into constant threat. A title like Blind Hunters of the Midnight Zone could easily become a parade of teeth. But teeth alone do not explain the Midnight Zone. Senses explain it. Scarcity explains it. Pressure, cold, current, and evidence explain it. The animals are not frightening because they break nature's rules. They are compelling because they obey rules that are hard for us to feel. The pressure at depth affects human equipment more obviously than it affects the animals. A submersible must have a pressure hull. Cameras need housings. Cables, seals, batteries, and syntactic foam must be engineered to survive compression. A tiny leak can destroy electronics. A window must hold back forces that the animal outside does not experience as an attack. This contrast is revealing. Humans enter the midnight zone as temporary visitors inside protective shells. The animals live there without shells of metal because their bodies are continuous with the pressure. They are not resisting the deep in the way we must. They are shaped by it. A research ship may spend hours lowering a vehicle through water before the real work begins. The descent passes through the sunlit layer, the twilight, and then the black. The cable pays out. The monitors show depth, temperature, altitude, heading. Somewhere below, animals are already hunting in darkness with no awareness that a machine is coming. By the time the ROV reaches them, the surface world is reduced to power, signal, and a line disappearing upward. Everything else is deep water. In the bathypelagic zone, body colors tend to be dark, red, or otherwise low visibility, but there are exceptions. Some animals are gelatinous and transparent, some are pale, some are reflective. Color depends on depth, lifestyle, and the kind of detection an animal is avoiding. A pale animal on the seafloor may live differently from a black midwater predator. The same is true of eyes. Reduced eyes in one lineage do not mean all deep-sea animals are blind. Some rely strongly on vision, others rely weakly. Some may use eyes mostly for detecting light and dark, rather than forming detailed images. The diversity is the point. When speaking about blindness, precision matters. A truly blind fish lacks useful vision. A functionally low-vision fish may still detect light. A deep-sea fish with small eyes may still use them for bioluminescence. A predator that hunts primarily by touch may still have eyes that provide some information. The word blind is powerful, but biology is usually more graded than language. For the purposes of this journey, the blind hunters are the animals whose lives show what happens when ordinary sight is no longer enough. Some have lost it. Some have minimized it. Some have moved beyond it. Some hunt the blindness of others. That last idea is especially important. A dragonfish with red light is not blind, but it moves through a world where many prey animals are blind to its beam. An anglerfish with a lure is not simply blind, it uses the attention of others. A tripod fish may be blind, but it occupies a current that delivers prey without requiring a visual chase. Darkness is shared, but advantage is uneven. The midnight zone is therefore not a world without seeing. It is a world of unequal seeing, partial sensing, and hidden signals. Predation here can be intimate. Touch at a fin ray. A lure a few centimeters from teeth. A mouth opening at close range. A scent followed until the source is near enough to bite. Without long-distance vision, many encounters become close before they become certain. This closeness increases risk. Prey may escape at the last moment. A predator may reveal itself too soon. Another animal may intercept the same signal. A missed strike wastes energy and may disturb the water enough to warn everything nearby. Energy budgets are central to understanding deep predators. Many deep-sea fishes have lower metabolic rates than shallow active fishes. They may have reduced muscle mass, slower growth, and lifestyles built around conserving energy. This does not make them weak. It makes them efficient under conditions where food is limited and temperature is low. A fast body is expensive. Continuous swimming is expensive. Large brains and complex visual systems are expensive. Every structure must justify itself through survival and reproduction. In the midnight zone, evolution often favors reduced cost, increased sensitivity, and the ability to exploit rare opportunities. This is why the animals can look unfinished to a surface observer. A narrow body, a soft body, a huge mouth on a thin frame, eyes that seem too small, fins that seem too long, skin that absorbs light. These are not incomplete versions of shallow fish. They are complete versions of deep ones. The shallow ocean is not the standard against which all life should be judged. It is only the part of the ocean we see most easily. Some deep-sea hunters use enormous gape. Others use protrusible jaws. Others use suction feeding. Opening the mouth rapidly creates a flow that pulls prey inward. In cold, dark water, the speed of a strike may still be decisive even if the animal's general lifestyle is slow. Ambush does not mean the final movement is weak. The mechanics of a strike are difficult to film at depth because they may happen quickly and rarely. High-speed observations are more common in laboratory or shallow water studies. For deep species, anatomy and occasional footage suggest the method, but many details remain inferred. Imagine a small fish approaching a lure. It does not know the shape behind the light. It detects a glow, perhaps movement, perhaps chemical cues. Then, the space behind the glow opens. Water rushes inward. Teeth prevent retreat. The light that meant possibility becomes the last visible point before darkness changes ownership. The event is brutal, but not evil. The anglerfish is not deceiving in a moral sense. It is feeding. The prey is not foolish. It is responding to signals in a world where signals are necessary and sometimes dangerous. Every prey animal in the midnight zone faces that dilemma. Ignore signals, and you may miss food or mates. Approach signals, and you may die. Flash light, and you may scare an attacker or reveal yourself. Stay dark, and you may remain hidden or fail to communicate. There is no perfectly safe choice. The predators face the same problem in reverse. Lure, search, wait, drift, or pursue. Each choice costs something. Life in darkness is a sequence of imperfect decisions made by bodies shaped before the moment arrives. The biological lights themselves are often blue-green because seawater transmits those wavelengths most efficiently. Red light from the surface is absorbed much sooner, which is why red animals can be effectively dark at depth. This creates the opportunity used by red light producing dragonfishes. The physics of seawater becomes part of the predatory system. In this way, the blind hunters of the midnight zone are not only biological subjects, they are optical subjects, hydrodynamic subjects, chemical subjects. Their bodies cannot be understood without the medium around them. Water is not background. It is the thing through which every signal must pass. A surface animal lives in air and often forgets the air is there. A fish lives in water and cannot forget. Water carries the body, resists the body, presses the body, cools the body, and informs the body. In the deep, where light fails, the other properties of water become more obvious. A pressure wave is a message written in water. A scent plume is a message dissolved in water. A flash is a message filtered by water. A current is a road made of water. The hunter reads these messages with organs that evolved to make them meaningful. Humans enter with instruments because our bodies cannot read them well. We need hydrophones, cameras, chemical sensors, CT scans, DNA sequencers, and pressure housings. We need ship time, weather windows, pilots, engineers, taxonomists, and patience. The animal needs none of that to live. It has its own instruments grown into its flesh. This does not make the animal mystical. It makes it biological in a way that challenges human assumptions. The deep sea is not magic. It is difficult physics inhabited by organisms that have had time to adapt. The lower boundary of the midnight zone, around 4,000 meters, leads into the abyssopelagic zone. There, the water remains dark, cold, and under even greater pressure. Some blind or low-light hunting strategies continue onto the abyssal seafloor. Others change as the seafloor becomes more important, and food supply often becomes even thinner. Abyssal predators and scavengers may rely heavily on smell, touch, and opportunism. The distinction between predator and scavenger may blur further. A fish may patrol slowly over sediment. An invertebrate may wait in a burrow. A sea cucumber may process sediment rather than hunt, while predators search among the animals that live on or in that sediment. The tripod fish sits near this transition in many people's imagination because it looks like a creature designed for the boundary between water and ground. It is a fish, but it behaves almost like a sensor platform. It raises itself above the bottom, samples the flow, and turns the passing current into a feeding surface. The image stays with us because it is so unlike a fast predatory chase. It shows that a hunter can be architectural. The body can become a structure placed in the path of food. A single tripod fish on a dark seafloor can make the ocean feel less empty and more precise. The sediment is not a blank floor. The current is not random. The animal is not lost. It is positioned. It is waiting in a way that only makes sense because unseen prey move through that exact layer of water. This is the kind of detail that changes the deep sea from scenery into habitat. The more specific the animal becomes, the less useful the word alien becomes. Alien is a tempting word, but it can distance the deep ocean from Earth. These animals are not alien. They are marine. They share ancestry with shallow organisms. Their molecules, muscles, nerves, and genes belong to the same planet. What is unfamiliar is not their origin, but the environment that shaped them. Calling them alien can be poetic, but it can also make them seem exempt from ordinary ecology. They are not. They need food. They avoid predators. They reproduce. They die. Their bodies decompose or become food. They are part of systems that connect to the surface through sinking carbon and migrating animals. The hidden ocean is hidden only from us. It is not hidden from the animals living there. For them, it is not the unknown. It is the place where signals have meaning, where currents have memory, where darkness has structure, where a point of light can be more important than a landscape. This is why a blind hunter can be perfectly at home in a place that would disorient a human instantly. As human activity reaches deeper, that home becomes less distant in practical terms. Fishing gear, cables, mining proposals, carbon changes, and waste all extend the surface world downward. The animals of the midnight zone evolved with pressure, darkness, and scarcity. They did not evolve with plastic fibers, persistent pollutants, industrial noise, or sediment plumes from machines scraping the seabed. The challenge is that damage can be invisible from the surface. A ship can leave an area, and the water above can look unchanged. But on the seafloor, tracks may remain. In the water column, particles may spread. In slow-growing communities, recovery may take longer than a human lifetime. This does not mean every deep-sea habitat is equally fragile in the same way, or that all human activity has the same impact. The details matter. Depth, substrate, species, current, disturbance type, and frequency all affect outcome. But caution is reasonable when ecosystems are difficult to observe and slow to recover. The blind hunters themselves may not be the direct targets of mining or fishing, yet they depend on the systems around them. Remove structure, alter prey supply, change oxygen, or disturb sediment, and the effects can move through food webs in ways that are hard to predict. A fish standing in current does not know policy. An anglerfish holding a lure does not know markets. A dragonfish using red light does not know the surface economy. But their future can still be shaped by decisions made far above them, by people who may never see them alive. This is one reason deep-sea footage matters beyond curiosity. It gives form to lives that might otherwise remain abstract. It is harder to dismiss a habitat once a body has appeared in the beam and shown that it belongs there. The animals in this script are not equally threatened, equally known, or equally common. Some are widespread. Some are rarely observed. Some live in midwater. Some on slopes. Some near the abyssal plain. The phrase blind hunters is a thematic grouping, not a taxonomic one. It includes different lineages that arrived at related strategies under similar pressures. Convergent evolution is common in the deep sea. Similar problems can produce similar-looking solutions in unrelated animals. Long sensory appendages, dark bodies, expandable mouths, reduced eyes, and luminous organs appear in different forms because the environment repeatedly rewards them. Convergence does not mean identical function. Two animals may both have long appendages, but one uses them mainly for touch, another for detecting chemicals, another for positioning, another for display. Two animals may both glow, but one hides with light while another hunts with it. Similar shapes need careful interpretation. This is why taxonomy, anatomy, behavior, and environment all matter together. The deep sea resists simple categories because the same darkness has many solutions. A blind hunter on the seafloor and a red light dragonfish in the midwater may never meet, yet they are connected by the conditions of the dark ocean. One extends feelers into current. The other extends light into darkness. Both are solving the problem of how to make prey detectable without spending more energy than the meal can repay. That calculation sits beneath almost every deep-sea predatory adaptation. The animal must not only catch food, it must catch food in a way that fits the economy of depth. Failure is part of that economy. A lure may be inspected and avoided. A shrimp may touch a fin ray and escape. A scent plume may lead to a carcass already stripped by competitors. A predator may rise toward a flash and find only a defensive signal. A mate may never be found. The deep sea is full of unsuccessful searches that leave no record. The records we have are biased toward success, because success leaves prey in stomachs, feeding marks on bodies, animals gathered at bait, and footage worth saving. But the long stretches of failure are just as important for understanding why these bodies are so economical. A predator built for constant action would starve here. A predator built for occasional success can persist. That persistence may look quiet, it may look strange, It may look, to a human viewer, like nothing is happening. But nothing is often the deep sea doing exactly what it does. The mouth of a deep predator is often described before the rest of the body, but sensory organs may be more important to survival. Teeth cannot help if prey is never detected. A stomach cannot stretch around a meal that never comes close. A lure cannot work if the animal cannot maintain position. Predation begins before the strike. This order matters in storytelling. The deep sea hunter is not a mouth with a body attached. It is a sensing system with a mouth at the point where information becomes food. In the ROV beam, this can be difficult to see. The light favors surfaces, teeth, eyes, skin, fins. It does not show the pressure wave passing over a lateral line. It does not show odor molecules. It does not show the sensitivity of a fin ray. It does not show what the animal knows before it moves. The visible animal is only the outer edge of an invisible sensory field. That invisible field may be the closest thing the animal has to landscape. Around the body, water carries gradients. Above, there may be faint biological light. Ahead, current may bring prey. Below, sediment may reflect turbulence. Behind, the animal leaves its own wake. The world is mapped not by sight lines, but by changes across the skin. To imagine this accurately is difficult, but the attempt matters. It keeps the deep sea from becoming only a spectacle of forms. It returns attention to the lived experience of the animal, as far as science allows us to approach it. We should be careful with that phrase, lived experience. We cannot know what a tripod fish feels, or what an anglerfish perceives, or whether a dragonfish's red-lit world has anything like a human sense of seeing. We can study organs and behavior. We can infer function. We can avoid pretending that our imagination is data, but we can still say that these animals are not passive objects. They sense, respond, feed, avoid, and reproduce. Their lives are active, even when their movements are minimal. In many deep sea fishes, swim bladders are reduced or absent, especially at great depth, because gas-filled spaces are difficult under pressure and costly to regulate. Buoyancy may be managed through tissues, lipids, reduced bone, and body composition. This affects how predators move and hold position. A slow-floating body with reduced skeleton can remain in the water column without constant swimming. For ambush hunters, neutral or near-neutral buoyancy is valuable. It allows the animal to hang in place, drift with minimal effort, or orient around a lure. For seafloor hunters, body density and fin placement affect posture. Anatomy and physics are inseparable. Jaw mechanics also reflect pressure and scarcity indirectly. A wide gape can accept larger prey. Inward-pointing teeth can stop escape. Elastic stomach tissues can accommodate uneven meals. But these adaptations come with trade-offs: skull strength, swimming efficiency, vulnerability, and developmental cost. The deep-sea predator body is not a collection of maximum features. It is a compromise that works often enough. This is why not every deep predator becomes huge-mouthed. Some remain small and precise. Some feed on tiny prey. Some specialize in scavenging. Some use speed in short bursts. The midnight zone contains many niches, not one universal design. A bristlemouth, for example, may be small, abundant, and part of the prey base for larger animals. Lanternfishes migrate and glow and feed and are eaten. Hatchetfishes use body shape and light. These smaller fishes are not all blind hunters, but they form the moving community that predators depend on. To understand the hunter, the prey layer must also be present. A dragonfish without small fishes is only anatomy. An anglerfish without curious prey is only a lure. A tripod fish without drifting crustaceans is only posture. The deep-sea predator is defined by what the dark water brings near it. Sometimes, what the water brings is not enough. Starvation is part of the deep ocean. Animals may die without leaving clear evidence of why. A weak fish may become food before it reaches the seafloor. A failed predator may be consumed by scavengers that follow its decay. The system recycles even its unsuccessful hunters. This is not cruelty. It is the movement of energy through a place where energy is precious. In that sense, every blind hunter is also temporary food. The teeth, lure, fin rays, and sensory canals will eventually stop working. The body will sink, drift, be bitten, colonized, dissolved, or buried. Other animals will find it through the same darkness it once used to find them. The hunter becomes a signal. The deep sea's carbon cycle depends on these transformations. Organic material produced near the surface sinks, is eaten, respired, repackaged, buried, or returned through food webs. The midnight zone is a major part of that processing. Predators affect how carbon moves, because feeding, migration, death, and waste all change the form and depth of organic matter. A fish eating a migrator at depth keeps some of that surface-derived carbon in deeper water. A predator's fecal pellet may sink further. A carcass may feed seafloor communities. The blind hunt is not only an individual event, it is part of planetary biogeochemistry, though the animal is not aware of that role. This connection between a tiny strike in darkness and the global carbon cycle can feel too large to hold together, but it is real. The ocean is not divided into separate stories of beauty, predation, climate, and geology. They are the same system viewed at different scales. A lure glowing beside a mouth is local. The food that makes the lure possible may have begun as sunlight and plankton near the surface. The waste after the meal may sink farther, feeding microbes or animals below. The event is small, but it belongs to the whole ocean. The midnight zone receives food from above, but it also sends animals upward. Many organisms migrate into shallower water under cover of night. They feed where food is richer, then descend before daylight increases predation risk. This daily migration links the surface and deep layers. Predators may follow, wait below, or specialize at the edges. Blindness is less useful in the upper twilight, where faint light and silhouettes still matter, but the boundary is not fixed. A predator may encounter different light conditions across its life or daily movement. Some larvae of deep-sea animals live nearer the surface before descending as adults. Life histories can cross layers even when adults seem tied to darkness. Larval stages are especially important and often underrepresented in popular accounts. A grotesque adult anglerfish may begin as a tiny larva in shallower water, looking very different from the adult form. Development changes the body as the animal enters deeper habitats. A hunter of darkness may not spend its entire life in darkness. This matters because adaptation is not only about the adult. Eggs, larvae, juveniles, and mating strategies all face different conditions. A species survives only if all stages work well enough. The deep sea can make adult bodies famous while hiding the younger forms that make those adults possible. A tiny larva drifting above the midnight zone may be as important to the story as the adult with the lure. It is just harder to recognize and easier to overlook. Every blind hunter was once something smaller, more vulnerable, and in many cases very different from the animal the camera later finds. Reaching adulthood in the deep sea is not guaranteed. Larvae may be eaten. Juveniles may fail to find the right depth. Adults may never find mates. The darkness does not only shape predation, it shapes every stage of survival. For species with extreme sexual dimorphism, this is especially apparent. A female may become the feeding body, the lure-bearing hunter, the larger organism. A male may become specialized for finding and attaching, sometimes losing much of what would be needed for an independent predatory life. The species divides the problem of survival into different bodies. This pattern is not universal across all anglerfishes, but in deep-sea serratioid anglerfishes it is one of the most striking reproductive adaptations. The small male may have enlarged sensory structures for finding females. The female may carry the lure and the feeding apparatus. In some species, attachment becomes permanent. In others, it may not. The diversity remains important. The reason behind it is not romance in the human sense. It is probability. In a vast dark habitat where individuals are widely spaced, finding a mate can be rarer than finding food. Once found, remaining together can improve reproductive success. A male anglerfish searching the dark is also a kind of blind hunter, though not hunting prey. It hunts a scent, a signal, a female body in a volume of water where missing her may mean never reproducing. Its smallness, its sensory focus, and its attachment behavior all come from the same deep-sea problem of distance. This broadens the title again. Hunting is not only feeding, it is searching for what life requires in a world that hides almost everything. A lure glows. A fin ray trembles. A nostril samples the water. A lateral line reads a passing pulse. A red beam slips across prey that cannot see it. These are not separate tricks. They are variations on a theme, how to locate meaning after sunlight is gone. The midnight zone is not silent in the sensory sense. It is only silent to us until instruments translate it. Human instruments, however, can introduce their own signals. Thrusters move water. Lights alter behavior. Metal frames reflect sound. Bait changes animal distribution. Even a lander sitting quietly on the seafloor is a new object with odor, shape, and potential shelter. Deep-sea observations must account for the possibility that the act of observing has changed the scene. This is why repeated observations are valuable. If tripod fish are seen again and again in similar postures across different places, confidence grows. If anglerfish lures are observed in multiple species and supported by anatomy, confidence grows. If stomach contents match predicted prey, confidence grows. Science does not need perfect access to build reliable knowledge, but it does need humility about limits. Some behaviors remain almost entirely unknown. Courtship, spawning, larval dispersal, detailed feeding frequency, daily movement patterns, and predator avoidance in many species are still poorly understood. The animals may be famous in images and obscure in biology at the same time. That contradiction is common in the deep sea. A creature can be visually iconic and scientifically mysterious. The picture travels faster than the data. The responsibility of narration is to slow the picture down, to ask what the teeth are for, what the eye can see, what the fin ray senses, what the lure costs, what the stomach contains, what the current carries. To let the animal be strange without making strangeness the only fact. A blind hunter deserves more than surprise. In the upper part of the midnight zone, predators may interact strongly with mesopelagic communities. Lanternfishes, bristlemouths, hatchetfishes, and shrimps move through layers where faint light and bioluminescence overlap. The predators that feed on them may use vision, lateral line, and bioluminescent cues together. Darkness at 1,000 meters is not the same as darkness at 4,000 meters. At greater depths, prey may be less abundant, and seafloor-related strategies become more prominent where bottom habitat exists. The animal community changes with depth, region, and proximity to structures. A title can unify the story, but the ocean remains varied. If you could remove the water, the midnight zone would still be difficult to comprehend. Mountains would rise from the seafloor, canyons would cut into continental margins, plains would stretch for enormous distances, trenches would drop below the average abyss. But removing the water would also remove the medium that makes the animals possible. The landscape of a blind hunter is not only rock and sediment, it is the water volume itself. That volume is where prey migrates, where particles fall, where signals travel, where a body can hang without touching ground. The deep sea is not a submerged land, it is its own kind of space. In that space, a hunter may never experience a horizon. It may not know up and down as a visual scene, but as pressure, gravity, light gradient, body orientation, and current. It may live suspended for years, with no shelter except darkness and no landmark except moving water. This kind of life is difficult for humans to imagine because we are creatures of surfaces. We stand on ground. we look outward. We measure distance by sight. The midnight zone hunter is a creature of volume, where distance is sensed through fading signals. The RUV light makes a temporary surface in that volume. It gives our eyes something to hold. But outside the beam, the water returns to its own terms. An animal may be only a meter away and invisible. A flash may happen behind the vehicle. A scent trail may cross the frame with no visible source. Every deep-sea video is surrounded by more ocean than it shows. This is why estimates of abundance and behavior cannot rely only on dramatic footage. Scientists need surveys, sampling designs, repeated transects, depth records, environmental context, and taxonomic expertise. A rare-looking animal in a video may be common, but seldom encountered by cameras. A common-looking animal at bait may be overrepresented because bait attracts it. Observation has to be interpreted. The deep sea forces science to separate visibility from existence. What we see is not the same as what is there. For blind hunters, that distinction is almost poetic, but it is also practical. Their prey may exist beyond vision. Their mates may exist beyond immediate detection. Their predators may exist outside the sensory range until they are close. Life is a constant negotiation between what is present and what can be perceived. Humans share that problem when studying them. We are also hunting signals in darkness. The difference is that our search is temporary. The animal's search is life. A deep-sea fish cannot return to the surface lab and discuss uncertainty. It cannot pause the descent. It cannot wait for better funding or clearer weather. It lives inside the conditions that make knowledge difficult for us. Some of the most revealing observations come from animals doing very little. A fish facing into current. A shrimp holding position near a vent. A squid drifting with arms arranged in a specific posture. A predator ignoring the RUV. These quiet behaviors establish baseline. Without baseline, dramatic moments have no context. For a blind hunter, baseline may be stillness, slow drift, or repeated orientation to current. The hunt may be less about pursuit than about being ready. Readiness is behavior. The moment of capture, when it comes, may be too fast to fully resolve. A mouth opens. A small body vanishes. Sediment lifts. The fish settles again. To the viewer, it may feel anticlimactic. To the animal, it is the difference between stored energy and continued hunger. The deep sea reduces drama to consequence. This is one reason the footage stays with people. It does not always explain itself. It shows an animal doing something simple under conditions that are almost impossible for us. A fish waiting in darkness becomes more memorable than a chase because the waiting contains the whole environment. The hunter is not separate from the midnight zone. It is the midnight zone made visible for a moment. The same principle applies to teeth. Teeth in deep-sea fishes often look oversized because the head and body may be small or delicate by comparison. Long teeth can trap prey that are slippery, soft-bodied, or nearly the size of the predator. They can prevent backward movement once the prey enters the mouth. In some species, teeth curve inward like a one-way gate. But teeth are only useful after detection and strike. A fangtooth with impressive jaws still has to encounter prey, orient toward it, and close the distance. The sensory problem comes first. A preserved fangtooth in a jar can look like pure aggression. Alive, it is a small fish in immense water, carrying a mouth that helps compensate for the rarity of opportunity. It is not attacking the world. It is prepared for the moment when the world comes close enough. This reframing does not make the animal less strange. It makes the strangeness more precise. Precision is also needed when discussing depth records. Many species have ranges, not fixed depths. A fish may be recorded from hundreds to thousands of meters, but records can come from nets that move through depth layers or from individuals outside typical ranges. Some animals move vertically. Some are found shallower as juveniles. Depth is evidence, not destiny. The midnight zone title points us toward the bathypelagic, but the animals connected to it may cross into twilight or abyssal layers. Their strategies often make sense across those transitions. The bathypelagic is also not the deepest ocean. Below it lies the abyss, and below the abyss in trenches lies the Hadal zone. In Hadal depths, pressure becomes even more extreme, and communities often depend on food funneled into trenches or produced through local processes. Blindness and non-visual sensing remain important, but the species differ. A film centered on the midnight zone should not pretend to cover all deep life. It should follow the theme where it belongs, while acknowledging that darkness continues below. The ocean does not end where sunlight ends. It changes, then changes again. The midnight zone is one chapter in a much larger vertical world. Within that chapter, blind hunters show how life keeps becoming specific under conditions that seem, at first, to erase specificity. Darkness erases color for us. It erases distance. It erases background. But for these animals, it reveals other things: the movement of water, the chemistry of decay, the pressure of a passing body, the location of a tiny glow. The sensory world is not gone. It has shifted. The shift is so complete that our first descriptions often fail. We say blind because we cannot imagine the replacement senses fully. We say monster because the mouth is easier to photograph than the ecology. We say alien because the environment is unfamiliar. Each word has some use, and each word can mislead. A better approach is to stay with the animal a little longer. Watch the posture. Ask what the fins are doing. Notice whether the eyes face upward, outward, or barely exist. Look at the skin. Look at the mouth, but then look past it. Ask what signal would cause this body to move. That question is the doorway into the midnight zone. What signal matters here? A flash, a touch, a scent, a pulse, a current, a shadow of bioluminescence, a chemical trace from a carcass, a vibration from swimming legs, a private red glow, a lure in front of teeth. Every hunter in this story is answering that question differently. The environment also answers back. A strong current can make hovering difficult, but bring more prey. A weak current can conserve energy, but reduce delivery. Sediment can hide animals, but also clog sensory surfaces. Low oxygen can exclude some predators, but favor others. Temperature can slow metabolism, but also reduce energy demand. The deep sea is a set of constraints that can become advantages depending on body plan. This is why there is no perfect hunter. There are only hunters suited to particular combinations of depth, prey, current, and signal. When conditions change, those combinations can fail. A shift in oxygen can compress habitat. A change in food supply can alter prey layers. A disturbed seafloor can remove structures used by animals that wait or hide. A new fishery can remove large individuals faster than they are replaced. The deep sea's stability is real in some ways, but it is not immunity. Animals adapted to slow, stable, low-energy environments may be especially vulnerable to rapid disturbance. Not always, not everywhere, but often enough to matter. Protecting the deep sea requires caring about animals that most people will never see alive. That is difficult. It asks for imagination disciplined by evidence. It asks us to value a fish standing in darkness on long fin rays, even if it has no obvious beauty by surface standards. It asks us to understand that hidden systems can still be essential. The blind hunters of the midnight zone are part of that argument, not because they are charismatic in a familiar way, but because their existence proves how much life has invested in conditions beyond ordinary human experience. A world that can produce a tripod fish, an anglerfish, a dragonfish, and 1,000 smaller unnamed interactions is not empty. It is not simple. It is not waiting for us to give it meaning. It already has meaning in the relationships between bodies, signals, and food. Our role is to notice without flattening it. There are also predators that live close to the sediment without the iconic posture of a tripod fish. Grenadiers, also called rattails, patrol many deep slopes and abyssal areas with large heads, tapering bodies, and strong sensory systems. Their eyes may be functional, but smell and taste are often important, especially when they approach bait or carrion. They are not always strict hunters. Many feed on a mixture of small animals, organic debris, and dead matter, which is exactly what a deep environment often rewards. A rattail moving over sediment does not need to see the whole plane. It samples. It follows. It dips the head. It turns when a chemical signal strengthens. It may take small crustaceans, worms, or fragments of larger bodies. In footage, it can look restless compared with a tripod fish, but its searching is still economical, guided by cues that are more chemical than visual. Watch one approach a baited camera, and the path rarely looks like a straight line drawn from intention. The fish enters the frame, leaves it, circles, returns, pauses with the head angled, then moves closer. It is following a plume that the camera cannot see. The odor has shape, but the shape is being stretched and torn by moving water. The animal is not confused. It is reading a signal that exists in pieces. This kind of movement is a reminder that the deep sea is not simply divided between active hunters and passive waders. Many animals do both. They search when a signal is worth following. They wait when searching would cost too much. They scavenge when death provides food. They hunt when living prey comes within range. The distinction between predation and scavenging can become especially thin in the deep sea because both depend on detection at distance. A living prey animal gives off motion, chemical traces, and sometimes light. A dead animal gives off chemical traces more strongly and may attract a community. A weakened animal may fall somewhere between the two categories. To the feeder, the important question may be less whether the food is alive and more whether it can be reached and consumed. This is not unique to the deep ocean, but scarcity makes the flexibility more visible. A large meal that arrives unexpectedly can reshape behavior around it. Animals that normally disperse may gather. Predators that normally hunt may scavenge. Scavengers may compete with predators. The deep sea is full of categories that make sense in textbooks and blur in the water. A bait fall on the seafloor shows this quickly. At first there is only the package, the camera, the dark, and the slow fall of particles. Then a fish appears from one side, then another. Amphipods arrive in numbers. Hagfish may coil and twist. A shark may pass through, changing the behavior of everything smaller. The food has made a temporary center in a place where centers are rare. For blind or low vision animals, that center is built by smell before it is built by sight. The first approach may begin far outside the beam. By the time the camera sees the animal, the hunt has already been underway as a chemical search. The same principle applies in open water, though it is harder to film. A wounded animal leaking chemicals into the current may become easier to locate. A swarm of small crustaceans may create a local pattern of motion. A dense, scattering layer may be detected acoustically by human instruments, but to predators it is a field of prey, flashes, and wakes. The midnight zone is not a uniform black sheet. It is textured by activity. Some textures are too faint for us. Others appear only when translated by sonar, or the behavior of predators themselves. Sonar has shown that layers of organisms can form in the water column, reflecting sound back to instruments. These layers may rise and fall with daily migration, and they can include small fishes, crustaceans, and gelatinous animals. Predators do not see a sonar layer, of course, but they may respond to the animals within it. Human technology reveals the pattern at one scale, the hunter experiences it at another. A dragonfish entering a prey layer does not need to understand the layer as a human graph. It needs to locate individual animals within the density. It may use eyes, lateral line, smell, or light. The layer increases encounter rates. The senses decide what happens next. Scale keeps changing in this story. A single copepod matters to a small fish. A small fish matters to a dragonfish. A dragonfish matters to a squid or larger predator. A migrating layer matters to carbon movement. A carbon flux matters to climate. The midnight zone hunt begins as a small biological event and expands outward into the functioning of the ocean. This is why the phrase hidden ocean is not just romantic. Much of what the ocean does is carried out by animals and particles that remain unseen by daily human life. The blind hunters are part of that machinery, not outside it. It is also worth remembering that many deep-sea species are known by names that emphasize strangeness: black sea devil, viperfish, fangtooth, gulper eel, ghost shark. These names are memorable, but they can shape perception before biology has a chance to speak. A name can make an animal sound malicious when it is simply adapted. The animals did not choose those names. They did not evolve to frighten us. They evolved under pressure, darkness, scarcity, and the problem of detection. A better narration can use the names without surrendering to them. A black sea devil is a small fish in a large dark ocean. A viperfish is a predator with teeth suited to holding prey. A fangtooth is not anger made flesh. A gulper eel is not a living appetite without context. These animals look extreme because the deep sea makes moderation look different. If they seem monstrous, it may be because the ordinary needs of life become visually unfamiliar when they are solved without sunlight. The same restraint should apply to the word primitive. Reduced eyes are not primitive. A simple-looking body is not necessarily primitive. A slow metabolism is not a failure to become modern. Evolution does not move toward human preferences for speed, sight, symmetry, or brightness. It moves through survival and reproduction in particular environments. A blind hunter in the midnight zone is not behind a shallow waterfish. It is adapted to another set of conditions. Its eyes may be reduced because large eyes no longer paid their cost. Its body may be soft because heavy structures were unnecessary. Its movement may be slow because speed was too expensive. This can be difficult to accept because humans are strongly visual animals. We trust eyes, we build cameras, we light the deep, and call the illuminated portion reality. But to an animal that lives there, our light may be the distortion. The normal world is the one without it. When the lights are off, a tripod fish still has its current. An anglerfish still has its lure. A rattail still has scent. A dragonfish still has signals tuned to its own eyes. The darkness is not a defect in their environment. The defect is in our access. Without machines, we cannot remain. Without lights, we cannot see. Without pressure housings, our tools fail. Without sampling, many details remain hidden. We are the visitors with incomplete senses, descending briefly into a place where the residents are already equipped. This reversal is important. It changes the emotional tone of the deep sea. Instead of a hostile void filled with bizarre survivors, it becomes a functioning habitat that is hostile mainly to us. Some deep-sea predators also use body orientation to control detection. A fish may hang vertically, head upward or downward, depending on its hunting strategy. A vertical posture can reduce silhouette, position the mouth toward prey moving from above, or make the animal resemble a drifting object. In midwater, where there is no bottom, posture can be camouflage and readiness at the same time. Orientation is rarely random. A predator facing into current is sampling what comes toward it. A fish angled upward may be watching for silhouettes or bioluminescent flashes. A body hanging head down may be placing sensory structures or jaws where they are most useful. The camera may capture only a pose, but the pose may be behavior. A pose can hold a life history inside it. The angle of a fin, the direction of a head, the stillness of a tail. In the deep sea, where overt action is rare, posture becomes evidence. It shows how the animal expects the world to arrive. For blind hunters, expectation is built into anatomy. Long feelers expect touch. Lures expect attention. Dark skin expects flashes. Large nostrils expect dissolved signals. Teeth expect escape attempts. Some of these expectations are easier to test than others. A lure can be observed attracting animals in footage, though not every approach proves deception. A bait plume can be tracked through animal arrivals. Fin rays can be examined for sensory structures. Eye anatomy can be compared with known light levels, but the internal decision-making of the animal remains out of reach. The more precise the evidence, the more respectful the uncertainty should become. Good science does not make the deep sea less mysterious by pretending everything is known. It makes the mystery sharper. The ocean below 1,000 meters contains more darkness than human history has ever illuminated. Every descent opens a small cone inside it. Every cone finds animals that have no need for the cone. Their bodies are explanations written in forms we are only beginning to read. A blind hunter is one of those explanations. It says that life can continue without image, without color, without horizon, without the daily cycle of light that organizes so much of the surface world. The surface still matters though, the plankton blooming above matter. The fish migrating at night matter. The dead whale sinking matters. The storm that changes surface productivity matters. The river that carries nutrients or pollutants matters. The deep is separate in experience, but connected in process. A predator waiting at depth is living partly on sunlight, transformed beyond recognition. The meal it catches may have fed near the surface days or weeks before. The darkness is not independent of the bright world. It is downstream of it. This connection makes food scarcity more complex. The midnight zone is not uniformly starving. Food can pulse after seasonal blooms. Migrating animals can move energy downward daily. Carcasses can deliver sudden abundance. Seamounts, canyons, and slopes can concentrate material. But compared with surface waters, energy is generally limited, delayed, and patchy. Patchiness shapes behavior. An animal that can survive lean periods and exploit pulses has an advantage. A hunter with flexible diet has an advantage. A predator that can detect prey at low densities has an advantage. Blindness is only workable when other systems compensate for the rarity of encounters. The compensation is never perfect. An animal can still miss the plume. It can arrive after others have fed. It can follow a light that is not prey. It can waste energy in a current that carries nothing. It can be detected by something larger. The deep sea offers solutions, not guarantees. That imperfection is what makes the animals real. Perfect hunters belong to myth. Real predators fail, wait, heal, starve, and try again if they can. Healing itself may be slow in cold, deep water, and injuries can change feeding ability. A damaged jaw, torn fin ray, infected wound, or lost sensory structure may matter greatly. Yet animals in footage often carry scars, missing pieces, parasites, or signs of past encounters. The deep sea is not a place where fragility prevents conflict. It is a place where conflict leaves quiet records. A missing fin filament may mean a failed predation attempt, a bite from a larger fish, abrasion from a net, or something else entirely. Interpretation is difficult. But the marks remind us that these animals interact physically with their world, not only symbolically with ours. Some scars are caused by humans before scientists ever see the animal. Trawls can abrade skin, break fin rays, rupture organs, and distort mouths. A fish on a deck may look like a creature from a nightmare partly because the journey upward has been violent. The deep animal has been translated badly. This is another reason in situ footage matters. It lets the body be seen before damage, suspended in the pressure and buoyancy that make it coherent. In place, a soft body may be graceful. A long jaw may rest naturally. A lure may hang with delicacy. Fins that collapse on deck may spread like sensors. The animal becomes less grotesque when the water is returned around it. The midnight zone cannot be understood by removing its animals from the midnight zone and judging them under fluorescent lights. At the same time, specimens remain essential. Without them, many species could not be described, compared, sequenced, or understood anatomically. The goal is not to reject collection entirely, but to recognize what each method gives and what it takes away. Observation preserves behavior. Collection preserves structure. Neither is complete alone. The best understanding of blind hunters will continue to come from combining careful collection, non-invasive imaging, long-term observation, experimental work, and honest uncertainty. The deep sea requires multiple kinds of attention. Attention is the opposite of spectacle. Spectacle asks for surprise and then moves on. Attention stays with the animal after surprise has faded. It asks what the body does, what the habitat demands, and what evidence supports the answer. A blind hunter of the midnight zone can survive spectacle, but it is better served by attention. Take the example of a deep sea fish with very small eyes. A quick description might say it cannot see. A closer one asks whether the retina remains functional, whether the animal detects light, whether it lives near the seafloor or in mid-water, whether it uses tactile structures, whether related species show similar reduction, and whether its stomach contents suggest ambush or search behavior. The first description creates an image. The second begins an investigation. The deep sea needs the second. The same applies to a fish with very large eyes. Large eyes do not mean the animal sees the world as we do. They may be tuned for faint point sources, silhouettes, or particular wavelengths. They may face upward to detect prey above, or forward to track flashes. Vision in darkness is not daylight vision made stronger. It is a different problem. This is why some of the most successful hunters after sunlight ends are not blind at all. They are visually specialized for a world where light appears as signal rather than scenery. But the title remains true because ordinary sight has lost its authority. Whether eyes are reduced or refined, they no longer dominate the world in the way human eyes dominate ours. Light is intermittent. Distance is uncertain. Other senses move forward. The hunter becomes distributed across its body. A mouth may close on prey because a fin ray touched it, a nostril found it, a lateral line detected it, or a lure brought it close. Vision may help or not. The decisive sense changes by species and situation. This variety is what keeps the midnight zone from becoming a single mood. It is not only ominous, it is not only still, it is not only strange. It is technical, biological, sparse, crowded in patches, dangerous, fragile, and deeply ordinary to its residents. A blind hunter is not a symbol of the unknown. It is an animal making a living. Making a living in the deep also means avoiding unnecessary exposure. Some predators may remain below prey layers until the right time. Some may use darkness to avoid larger hunters. Some may reduce reflective surfaces. Some may position themselves near sediment or structure. Risk management is as important as feeding. The best predator is not the one that attacks most often. It is the one that feeds enough while surviving long enough to reproduce. In the deep sea, survival may depend on refusing action as much as taking it. Refusal is hard to show on camera. The animal that does not strike leaves no dramatic clip. The fish that ignores a lure, avoids bait, or remains beyond the lights may be behaving wisely, but its wisdom is invisible to us. Deep sea footage is a record of appearances, not absences. The lives beyond the frame may contain more caution than we know. There are also sensory conflicts. A prey odor may come from the same direction as a larger predator. A flash may signal both food and danger. A current may bring food, but also carry the hunter's own scent away. The animal must respond without certainty. Nervous systems evolved for such habitats do not need perfect information. They need useful thresholds. Those thresholds are shaped by natural selection. Strike too often at false signals, and energy is wasted. Strike too rarely, and food is lost. Approach every odor, and risk increases. Ignore odors, and meals are missed. Deep-sea behavior lives between hunger and caution. This balance may be one reason many deep predators appear almost suspended in hesitation. They are not indecisive in a human sense. They are tuned to conditions where the wrong movement can cost more than waiting. In the midnight zone, stillness can be a form of intelligence built into the body. The animal does not think through equations, but the equation is there, written by evolution into posture and response. The equation changes when humans add bait, noise, light, or disturbance. A baited camera creates an artificial abundance. A trawl creates injury and carrion. A mining test could create sediment clouds. A submersible light creates a temporary sun. Deep-sea animals may respond strongly because such events are unusual at their scale. This does not make observations useless. It means observations must include the disturbance as part of the scene. In a way, every deep-sea film is a collaboration between the animal and the intrusion. The animal brings its body and behavior. The machine brings light and presence. The footage is real, but not untouched. Understanding begins when that is acknowledged. A blind hunter filmed under artificial lights is still a blind hunter. But the frame should not be mistaken for the whole darkness. The whole darkness remains beyond the lamps, carrying signals no microphone, camera, or narrator fully captures. Somewhere a fish waits through hours no one records. Somewhere a plume spreads from a body no one finds. Somewhere a lure glows and goes unnoticed. Somewhere prey pass just outside a sensory field and survive. These unseen non-events are part of the deep sea too. It may be that the most important thing about the midnight zone is not how strange it is, but how complete it is. Complete without sunlight. Complete without plants. Complete without landscapes visible to human eyes. Complete with food webs, senses, predators, prey, reproduction, death, and recycling. The blind hunters prove that completeness. They show that the end of light is not the end of ecological complexity. When we describe the midnight zone as dark, we are stating a physical fact. When we describe it as empty, we are usually describing our own instruments, expectations, or impatience. The animals contradict the emptiness, not always with abundance in a single frame, but with adaptation across millions of lives. A single reduced eye, a single sensory ray, a single lure, a single stomach containing prey, each is evidence that darkness has been occupied and solved in many different ways. The solutions are not loud. They do not announce themselves from the surface. They drift, wait, glow, sample, and strike in water that absorbs almost everything we send into it. The deep sea keeps most of its motion private. But private does not mean unreal. There are places in the deep sea where the boundary between habitats is visible even without sunlight, once a camera brings light to it. A brine pool on the seafloor can appear as a dark lake within the ocean, its dense, salty water settling into a depression and forming a sharp interface with the seawater above. Animals may gather along the edge, not because it is safe in a simple way, but because chemical boundaries can concentrate life and death. A hunter near a brine pool is dealing with a physical edge very different from a reef wall or canyon slope. The dense brine can be toxic or inhospitable to many animals. Bodies that enter may be stunned or killed. Scavengers and predators may patrol the margin, where the boundary creates opportunity. In darkness, chemistry becomes geography. The edge of a brine pool shows how a blind hunter can use a line it may not see as a visual line. It may detect chemistry, current, struggling prey, or the presence of other feeders. To the camera, the pool looks like a surface. To the animal, it may be a gradient of danger and food. This is one more reminder that the deep seafloor is not only sediment and emptiness. It contains chemical lakes, seep fields, vent chimneys, carbonate crusts, burrows, drop-offs, and carcasses. Each feature changes how animals search and wait. Trenches add another dimension. Much of the Haddle Zone lies below the bathypelagic and abyssal zones, deeper than the main Midnight Zone range, but trenches can funnel organic matter downslope and concentrate food in ways that matter to deep animals. Landslides, currents, and gravity move material downward. Scavengers and predators in these systems may rely heavily on smell, touch, and opportunism. The pressure there is far beyond what ordinary equipment can endure, and yet amphipods, fishes, microbes, and other organisms live in those depths. Their sensory worlds are not well known compared with shallow animals. But the same principle holds: where light cannot guide, other signals become central. A trenchfish, a sea predator, a slope scavenger, and a midwater anglerfish may never share the same habitat. But all belong to the larger story of animals finding food under conditions that erase the easy assumptions of sight. The darkness changes the rules, and different places add their own complications. The Midnight Zone is the center of this story, but the deeper ocean around it keeps echoing the same question: how does life find life when the world cannot be seen? Sharks and rays bring another sensory system into the discussion. Many cartilaginous fishes can detect weak electric fields produced by living organisms using sensory organs around the head. In deep water, some sharks and chimeras use smell, lateral line information, and electroreception as part of their search for prey or carrion. They are not usually blind in the simple sense, but they show how vision becomes only one element in a broader sensory toolkit. A deep-sea shark approaching bait may follow odor across distance, then use closer-range senses as it nears the source. Its movement can seem slow and deliberate. The head sweeps. The body turns. The animal is narrowing a field of possibilities. A camera captures the final approach, but the search began before the shark entered the light. Not every deep-sea predator has electroreception, and not every sensory claim applies across groups. Bony fishes, sharks, cephalopods, crustaceans, and worms differ profoundly. The phrase "blind hunter" should never flatten those differences. It should open them. One of the most important lessons of deep-sea biology is that similar environmental pressure does not produce one solution. Darkness can lead to reduced eyes, larger eyes, chemical sensing, mechanical sensing, lures, counter-illumination, stealth coloration, or combinations that do not fit a simple list. The animals are not variations on a monster, they are variations on attention. One attends to current, one attends to light, one attends to smell, one attends to touch, one attends to the electric trace of a body, one attends to the fall of food from above. The Midnight Zone is a place where attention has become anatomy. This is why the face of a blind hunter can be so revealing. In surface animals, the eyes often dominate expression. In deep animals, the face may be reorganized around other needs: nostrils, jaws, barbels, lures, sensory pores, or structures that seem strange only because they are not meant for our kind of reading. A small eye beside a large olfactory organ is not a mistake. A mouth larger than the skull seems possible at first glance is not exaggeration. A chin barbel sweeping sediment is not ornament. The face is a map of priorities. Priorities are shaped by depth, but also by size. A tiny predator experiences water differently from a larger one. Viscosity, turbulence, swimming cost, prey size, and detection range all scale with body size. A small crustacean's movement may be a major signal to a small fish and almost nothing to a larger predator at distance. A large carcass may be irrelevant to a tiny filter feeder and overwhelming to scavengers that can consume tissue. The Midnight Zone is therefore layered by scale as much as by depth. What counts as prey, danger, or signal depends on the body receiving it. For a small hunter, the world may be dense with nearby pulses. For a larger one, it may be sparse and widely spaced. For a scavenger, a carcass odor can dominate everything. For an ambush fish, a single touch on a fin ray may be enough to trigger the only movement that matters all day. There is no single sensory darkness. There are many darknesses, each scaled to a body. This may be the closest we can come to imagining the midnight zone without making it ours. Not as a black room, not as a void, not as an alien kingdom, but as overlapping sensory worlds. A place where one animal's invisibility is another animal's signal. A place where blindness is sometimes a loss, sometimes an economy, sometimes a weapon used against the blindness of others. The animals do not need the whole ocean to be knowable. They need enough of it to respond. A final piece of the story is time. Deep sea animals often live in slower rhythms than shallow animals, but slow does not mean inactive. It means events may be spaced differently. Feeding, growth, reproduction, and recovery can unfold on timelines that do not match the expectations created by surface footage. A 5-second strike may depend on days or weeks of waiting. A reproductive encounter may depend on years of survival. When humans edit deep sea footage, time is compressed. Waiting is removed. Empty frames are cut. The animal becomes more dramatic than its life may usually be. A truthful script has to restore some of that waiting. Waiting is not emptiness. It is the condition that gives the strike meaning. A lure glowing for hours, a fin ray extended into current, a fish cruising through a plume, a predator ignoring weak signals until one becomes strong enough. These are the true rhythms of blind hunting, and beneath those rhythms is the immense stability of dark water. The surface may change with weather and season, but at depth the daily world is buffered, cold, compressed, and dim. This stability allows delicate sensory systems to matter. A small disturbance can stand out because the background is often quiet enough, or at least consistent enough, for the animal to detect it. The deep sea is not always calm, and currents can be strong, but its darkness removes many of the visual disturbances that dominate shallow water. The hunter's world is difficult, but it is not chaotic in every sense. It has patterns that bodies can learn through evolution. To say a body learns through evolution is not to say an individual understands the pattern. It means individuals with useful responses survived and reproduced more often over many generations. The result is behavior that appears purposeful because it has been tested by consequence. A tripod fish does not need to know why facing current works. The individuals that did it well ate enough. The posture remained. This is the quiet power of these animals. Their bodies carry decisions made by death and survival long before any humans saw them. Every reduced eye, every feeler, every lure, every dark surface is part of that record. The record is still being written in the midnight zone, in darkness, one encounter at a time. Even the word hunter should be held carefully. It suggests action, pursuit, and control. In the midnight zone, hunting may be closer to participation in a field of probabilities. The animal positions itself where a current improves the odds, carries a signal that may draw prey, follows a plume that may lead to food, or waits for contact that may never come. It is active, but not always visibly active. This kind of predation can feel almost mathematical, not because the animal calculates, but because the body has been shaped by repeated outcomes. How much energy can be spent? How close prey must be before a strike is worth attempting? How bright a lure can be without attracting too much danger? How long a fish can remain still before moving becomes necessary? The answers are written into form and behavior. When the camera catches one of these answers, it is easy to focus only on the strangeness, but the stranger fact is that the answer works. In a world without daylight, without plants, without easy meals, life has found ways to turn darkness into information. There is another reason to leave room around the word blind. Some animals that look visually reduced may still respond to light in ways that matter. Detecting the difference between total darkness and a nearby flash is not the same as seeing a detailed image, but it can still guide behavior. A tiny light-sensitive organ may tell an animal when something has moved, when a lure is nearby, or when another organism has produced a defensive burst. For a human, that might not feel like seeing. For a deep sea fish, it may be enough. The difference between image and signal is central here. The midnight zone does not offer scenery. It offers events. An event can be very small. A copepod flashing as it escapes. A shrimp brushing a sensory ray. A fish disturbing a layer of still water. A speck of carrion releasing scent into a current. The hunter does not need a complete picture of the world if the event carries enough direction. This is why so many deep-sea adaptations seem exaggerated when isolated and sensible when returned to context. The enormous mouth, the dark skin, the small eye, the glowing lure, the long ray, the sensitive nostril. Each one increases the chance that a rare event becomes usable. But usable does not mean safe. A predator following a signal may become the next signal for something else. The water remembers movement briefly. A flash travels outward. A scent spreads. A struggle can call attention. In darkness, every act of feeding may create information for other animals. The midnight zone is therefore full of hidden feedback. A successful strike may attract competitors. A carcass may gather scavengers and predators. A lure may draw prey and risk. The animal feeds inside a web of consequences. That web is why the deep sea should never be imagined as empty space with isolated monsters. It is a community, even when the members are far apart. They are connected by falling food, dissolved chemicals, migrations, predation, reproduction, and death. A blind hunter is one thread in that community, not a creature outside it. Near the end of a dive, the rove may lift away from the seafloor or begin its long ascent through black water. The lights still catch snow. The cable still leads upward. The animals remain below. A fish that was visible for a minute returns to a darkness that is not darkness to it in the same way. The camera leaves with images. The hunter remains with current, pressure, and hunger. Above, on the ship, people will replay the footage. They may identify the species or leave it uncertain. They may mark the behavior as feeding, resting, responding, or unknown. They may compare it to previous dives. The clip may later appear in a documentary, trimmed to a few seconds, surrounded by music and narration. But the actual encounter was quieter than that. A machine entered. An animal was seen. The ocean continued. That continuity is the final point. The midnight zone does not depend on human attention. Its hunters lived before cameras reached them, and they continue outside every frame. Scientific discovery does not create them. It changes our relationship to them. When we call them blind, we should remember that we are describing the limits of vision in a place where vision is only one sense among many. They are not lost in darkness. They are adapted to a world where darkness is normal. Somewhere below the last sunlight, a fin ray is extended into current. Somewhere, a lure is glowing near a mouth. Somewhere, a dragonfish is using light that most prey cannot see. Somewhere, a scavenger has turned into an odor plume and is following death toward food. Somewhere, a small flash has betrayed movement and a predator has turned. None of this requires a horizon. None of it requires daylight. It requires only the ancient exchange between hunger and information. The blind hunters of the midnight zone are not blind to their world. They are blind only to the kind of world we expect. Their darkness is full of direction. Their stillness is full of waiting. Their strange bodies are not accidents, but records of what the ocean demands when the sun is gone. And when the camera light finally fades behind them, they do not enter emptiness. They return to the water that made them readable to themselves, long before they were visible to us.